A quiet welcome unfurls in the room as if the air itself offers a soft invitation. Someone sits in a pool of lamplight, perhaps near a window, where the night holds its breath and the world outside slows. No voice speaks, yet a calm suggestion gathers, be warm, be unhurried, and follow a question that moves like tide did Earth once turn under two moons. The scene holds in third person, present unbroken. Outside, the planet rolls through its ordinary rotation, one pale companion riding the dark. But memory in rocks and models opens a door to fire and dust, to a time when continents do not yet exist, when oceans are vapour, and the sky wears a glow no modern evening remembers. In that early heat, Earth is young and fast, its crust a restless skin, and a Mars-sized body, later given the name Theia, meets it in a glancing world-scale collision. Ejecta arcs upward, as incandescent rain, silicate vapour, and molten droplets forming a bright ring that circles the wounded planet. From this ring, gravity collects fragments, and within a few months to a few decades, a quickness by geological clocks, the first mass of the moon coalesces an ember that cools towards stone while Earth's surface seethes below. This is the accepted spine of the story, a giant impact origin for the moon, supported by the scientific fact that lunar and terrestrial rocks share nearly indistinguishable oxygen isotope ratios, a chemical closeness that folds the moon into Earth's mantle history, even as it drifts apart by centimetres per year. The ring is not smooth. It clumps, wakes and braids, and in certain simulations a lesser body gathers too, a smaller offspring of the same splash, trailing or leading the newborn moon, in a gentle offset like a pale thought following a brighter one. The lesser companion is no certainty, only a possibility with numerical breadth, but the image remains two children of one fire circling a hot Earth under an orange sky. Above the molten basins, Earth's days run short, perhaps 5 or 6 hours long. Tides rise in fast pulses, and the near vacuum above the glowing ocean carries curtains of silicate clouds. A lesser-known real-world detail from far later whispers backward to this scene in banded sedimentary rocks called tidal rhythmites. Ancient layers record that Earth's day once counts fewer hours, a fossil clock of tidal friction that lengthens the day and sends the moon outward. The stone remembers a rhythm that fits the broad mechanics of this birth. The larger infant moon settles into synchronous rotation. One hemisphere always faces Earth while the far side faces away forever. On its cooling crust, a magma ocean crystallizes. Flotation of plagioclase builds a light anorthositic crust, thicker where cooling proceeds, gently thinner where heat lingers. The smaller companion, if it exists, wanders near a stable point, and then slips from it as resonances nudge. Orbits adjust precess and trade angular momentum with Earth's tides. The two pale bodies circulate in uneasy harmony, their paths not colliding, yet not quite apart. A quiet scientific mystery holds centre. Even in this calm telling, does that smaller moon truly exist for millions of years, or is it a transient clump that dissolves under the tide? The hypothesis known as the two-moon, or big splat idea, proposes a low-velocity accretion of a small companion onto the bigger moon, emerging so slow that stone does not shatter, but smears building thickness on the far side like plaster laid at walking speed. Evidence is circumstantial, lopsided crustal thickness, a high plateau of far side highlands, compositional contrasts, but the certainty remains gently out of reach. Night returns to the window. The one living moon outside carries a familiar face. Dark Maria composing a pattern, the eye learns early. An irony follows soft and sleepy. The hemisphere that seems more complex in shadowed seas is the one Earth always sees, yet the truly thicker, rougher crust lies forever turned away. Another quiet irony. The satellite that keeps Earth's tides in a metronome drifts outward every year, so the force that orders the water slowly weakens the bond. And a third small irony, almost amuse the moon that looks separate in the sky, is by isotopes, almost Earth in exile, a piece of the planet that learned to be distant without being different. The early heavens glow. Earthshine sunlight reflected from a hot, bright Earth paints the infant moon's night side with a fierce, ruddy light, turning darkness into a false day. The small companion, if present, shares that glow a faint bead, a few planetary diameters away from the larger disk. Tides in Earth's young magma ocean answer both masses, and the planet's spin yields a surplus of energy that shifts orbits imperceptibly but relentlessly. Resonances appear and vanish as distances change. The smaller orb finds itself shepherded toward a location ahead of or behind the main moon by a fixed angle, a Trojan-like repose that is stable only in certain models and only for a while. Time steps silently through millions of years. The big moon's near hemisphere stays warm longer because Earth's radiance and tidal heating favour it. The far side, less favoured by heat, grows thicker. Crust. Asymmetry becomes a habit. In the hypothesis of two moons, a slow merger one day begins. The smaller companion approaches not as a bullet but as a snowdrift velocity, low enough perhaps a few hundreds of meters per second. That shock does not melt oceans of rock, but rather piles buoyant thick anorthosite and cools as it lands. The far side receives an added blanket, and the memory of this quiet collision endures as highlands that rise and rise again into rim and plateau. A gentle, modern analogy passes without overstaying. It is as if a second scoop of pale plaster is pressed onto one face of a half-finished sphere and left to harden, leaving weight on one side and smoothness on the other. Gravity notices, but not enough to undo it. The narrative remains restrained. The two-moon merger is not consensus, only a tolerable speculation that fits several pieces. Alternate scripts keep their chairs at the table, asymmetric tidal heating by a young close moon. Concentration of radiogenic elements on the near side producing prolonged melting and Maria. Ancient bombardment distributed unevenly. Each explanation writes a different order of cause and none violates physics. The mystery is an old friend here, seated politely near the lamp. The listener remains still. The scene makes room for small facts that clear the air. The moon's distance today increases by about 8 centimeters each year as measured by laser ranging to corner reflectors left by astronauts. An exquisite testimony to tidal friction. The lunar far side's crust is on average markedly thicker than the near side's, a measurement strengthened by gravity mapping from orbit. The oxygen isotope similarity between Earth and Moon sits within a few parts per thousand, much closer than most meteorites from other parent bodies. These measured truths do not demand a lost moon, but they leave a silhouette into which a lost moon can fit. In the cooling night of the Hadean and early Archean steam condenses ocean's rain from ski basalt plains on the near side flood, as mare lavas later in time while the far side highlands keep their bright ancient scars. The planet stabilizes under a calmer spin, its day lengthening by tidal drag. Coral fossils much later will fold this slow arithmetic into their very growth rings. A detail from deep time that lets modern eyes read a clock older than cities. A gentle uncertainty shades the window again if a small companion once existed. How long does it persist before the soft embrace? Are there traces of its core, its distinct chemistry, buried under the far side's miles of light rock? Does any basin align with such a meeting place? Seismometers left in the 20th century hear moonquakes and thumps from thermal cracking and impacts, but their sparse network cannot disclose deep ancient sutures. Future instruments may listen better, but the present story accepts ignorance without impatience. In the room a breath, a pause, the world keeps turning. An observer notices that nothing in tonight's sky hints at a former twin, and that is as it should be. The sky favours present tense. The rocks carry the past. The patient tone remains even. There is no drama to resolve, only a series of soft balances between certainty and inference, between maps and memories, between a hypothesis that explains why the far side is a mountain, and an alternate that explains it differently. Another trio of small dry observations drifts through like thin clouds. It only takes one impact to make a family and a lifetime of models to keep it tidy. It only takes a few overlapping explanations to make a debate feel like a landscape rather than a fight. And it only takes the hidden hemisphere, the one that never faces Earth, to carry the loudest geological clue. Under the single moon outside, tides pull at coasts with ordinary strength, and the companion slides a little farther away. The lamp continues to glow. The listener, unworried, remains awake inside a question that prefers to move slowly. The story's rhythm stays flat and contemplative. Images repeat to keep company, plagioclase crystals floating like pale ice on a crimson sea. A second little globe keeping station for a time. A coat of rock settling with the grace of a snowfall. The far side bright and thick, the near side dark and thin. The same isotopes breathing through both worlds as if they were one body held apart by distance. No conclusion is demanded. The section holds the idea like a specimen in gentle light, and then sets it down exactly where found. Only took a single ancient blow to place a gentle hypothesis in modern minds. Only took the moon's refusal to show its backside to make its loudest difference invisible. Only took centimetres per year to turn a day of 6 hours into one that fits a workday and an evening like this. When impact made a companion, the scene is not violence for its own sake, but a rearrangement of heat rock and angular momentum that leaves the young Earth altered and accompanied. In third person present, the early planet turns under a dimmer sun, its mantle hot, its crust a restless scab, and a Mars-sized protoplanet, later named Theia, approaches on a crossing trajectory set by the slow arithmetic of accretion, migration, and chance. The grazing collision unfolds in minutes, yet writes its consequences for billions of years. Cores glance, mantles interpenetrate, and a fountain of silicate vapour and melt vaults into a canted orbit around Earth. Too hot to be dust, too cool to be star, a circumplanetary cloak that glows like a low sky. The scientific fact at the spine is sober and precise. The moon's bulk composition and near identity of oxygen isotopes to Earth's mantle, along with angular momentum of the present Earth-Moon system, are best explained by a giant impact that leaves a debris disk outside Earth's Roche limit, where gravity can gather clumps. Inside the Roche limit, tidal forces forbid accretion, and instead grind fragments into rings that feed the outer nursery. In some simulations, the collision creates not merely a disk, but a brief synestia, a swollen, vaporized donut-like envelope where rock behaves like gas, a continuous hot atmosphere of silicates threaded by liquid droplets, which then cools and condenses raining stone into a disk that continues to breed a satellite. Whether synestia or simpler disk, the result converges within months. To decades, a primary moon coalesces beyond roughly 3 Earth radii, while the inner ring decays and replenishes the outer reservoir, a conveyor that fattens the newborn body. Beneath this broad picture, a lesser-known tactile detail hides in crystals, as the magma ocean on the newly formed moon cools buoyant plagioclase, floats upward to form a light anorthositic crust, Ferroan anorthosites, that Apollo samples later date to over 4 billion years. Pale rock that becomes the backbone of the highlands, the naked eye still sees as a chalky shine. Microscopic zircons locked in these rocks carry time as atoms, and their ages read like embers that refuse to go out. Meanwhile, Earth's mantle reels, and then settles into new convection. Its rotation possibly shortened to 5 or 6 hours per day, tides heaving under a moon that orbits close enough to fill a quarter of the sky. Tidal friction begins its long, patient work, bleeding spin from Earth into orbital distance for the moon, an energy exchange measured today by lasers bounced off corner reflectors, to a fidelity fine enough to notice millimeters of night, an echo from astronaut hands left in dust. The physics of that first hour is clean in outline and stubborn in detail. The impact angle that best preserves angular momentum is oblique. The partitioning of iron determines whether Theia's core merges with Earth's or liberates metallic droplets into the disk. The temperature field sets how thoroughly silicate vapor and melt mix, and that mixing matters because of a quiet crisis. The hypothesis once faced the isentropic sameness of Earth and Moon, suggested either a Theia, almost indistinguishable from Earth, unlikely among solar neighbours, or a vigorous equilibration between vaporized Earth mantle and disk. Modern models answer with both possibilities: a Theia with Earth-like isotopes born near our orbit, plus turbulent mixing in a hot post-impact envelope that homogenizes oxygen, titanium and tungsten signatures before condensation locks them in. A gentle analogy appears and leaves the impact is not a billiard shot, but a slow stir of red syrup and amber honey that then cools into a single pale candy with faint swirls too subtle to see without dissolving it again. A mystery remains in polite outline. The exact angular momentum budget of the newborn system must relax to today's value. High angular momentum variants of the impact require a subsequent tidal resonance with the Sun, the evection resonance to bleed off excess, while canonical impacts need less later tailoring. Which path is truer is left open because dynamics over tens of millions of years inside a changing disk answer to parameters still unmeasured with certainty. Above the hot planet, the disk stratifies melt droplets, follow orbits that collide and coalesce while vapor cools into condensates that rain to the midplane. Clumps grow by sticky encounters until self-gravity rounds them. Shepherding resonances shape wakes and gaps and numerical moons. 2 or 3 at first compete and merge until one wins. The nascent satellite migrates outward as talks between disk and moon. Trade angular momentum, a slow launch that ends only when the feeding zone thins to nothing. 3 soft ironies drift like ash in warm air. The collision that seems to threaten Earth most becomes the event that stabilizes its long-term climate by giving it a large moon that damps chaotic swings in obliquity. The act of destruction yields a companion that will later preserve delicate histories in a vacuum better than any archive on the ground. And the one satellite that looks least like Earth in the sky, pale airless cratered turns out by isotopes to be the one most like Earth in the solar system, a fragment bearing the planet's own chemical accent. In the cooling aftermath, Earthshine lights the lunar nights with a false ruddy day. The young moon's magma ocean, hundreds of kilometers deep, convects lazily as heat escapes to space. Cumulate layers settle, dense ilmenite-rich deposits sink, and incompatible elements, potassium, rare earths, phosphorus and radioactive heat producers concentrate in a residual melt called creep. Later, when crust thins and fractures, creep-rich regions on the near side favour volcanism that will flood basins with dark mare basalt, setting up an asymmetry that maps today's face. The cosmic ledger accepts that this asymmetry does not require a second moon, but it leaves room for one. If, as some models suggest, a smaller co-orbital body persists at a Trojan-like point, 60 degrees ahead or behind the main moon, gravitational whispers from the Sun and tides from Earth eventually destabilize the sanctuary. The small companion drifts a patient wander, and in a few tens of millions of years it approaches the larger moon at relative speeds gentle enough to avoid global melting. It plasters the far side with extra thickness, an idea framed by the big splat hypothesis, not inevitable, not consensus, but compatible with the stark highland plateau that no living eye sees from Earth. Another lesser-known human-scale detailed breccias gathered by Apollo astronauts contain tiny glass spherules that record impacts into hot, thin atmospheres, lunar fire fountains that once sprayed droplets arcing ballistically across low gravity. Some glasses carry tinier bubbles, still witnesses to eruptive volatiles trapped in a world that otherwise has no air. Those beads are the cooled punctuation of a planetesimal-sized event that set every subsequent sentence. Through this long, even narration, mechanics keeps its posture. The Roche limit fixes where rubble can clump. The Tumra-Q parameter whispered from galactic disks to this small ring decides when self-gravity overcomes pressure and shear. The conservation laws of mass and angular momentum tally every splinter and vapor wisp. Heat capacity and latent heats decide how fast lava oceans congeal. And when numbers are propagated forward, Earth's day lengthens by tidal friction. The moon recedes and stripes of tidal rhythmites, recorded in much later sediments on Earth, quietly agree with clocks that nobody set. 3 more soft ironies drift across the hot horizon. The ring that forms from chaos must cool with exquisite restraint to make a single placid satellite rather than fragments. So serenity depends on how slowly the fire dies. The moon that will one day host mirrors for laser ranging owes its precise role as timekeeper to the very tidal breaking that steals time from Earth's spin. And the clearer the models become in headlines, the more they confess what they cannot yet pick impact angle within a few degrees, Thayer's exact mass, the depth of mixing. So precision increases the catalogue of uncertainties rather than shrinking it. In laboratories, tungsten 182 isotopes remember the decay of hafnium 182, a short-lived nuclide from the solar system's first few tens of millions of years. Differences in this chronometer between Earth and Moon are small, another nod toward thorough mixing or similar parentage. Chromium and titanium isotopes, too, sing a near-twinship that leans away from capture theories and toward impact. Capture would require impossible energy loss without an atmosphere, and would leave the isotopic accent wrong. Fission from Earth scenarios fail angular momentum. Only an impact carries both plausibility and parsimony to the table. The scene in this telling never hurries. The listener remains in lamplight while the planet above the roof receives a satellite below the threshold of sight and above the threshold of permanence. Volcanic plains on the eventual near side have not yet poured. The far side and orthosites float and thicken. The debris that cannot join the moonlet rains back as shooting stones across a sky that glows peach from a hot Earth. Each rain leaves a bruise that later Mascon's mass concentrations under basins will reveal to spacecraft as tiny tugs on orbit's gravity's memory of ancient hammers. A quiet uncertainty kept honest by maps and models keeps its seat. Was Thayer's composition nearly identical to Earth's, because it formed at a similar heliocentric distance, or did the post-impact vapor shroud mix so thoroughly that chemical accents blurred? Which version makes the far side's thickness easier to draw without violating heat flow? How long did the disk persist hot enough to equilibrate isotopes? Are there lingering kernels in the moon's deep mantle that keep a distinct signature? Seismology from sparse stations hints at layers, yet full answers await future networks that can triangulate moonquakes the way Earth's arrays do under continents. The story remains a flat sea without waves. The section leaves the impact where it belongs, not as spectacle, but as an organising episode in a calm history. A body of nearly Earth's size falls just so. A ring blooms and cools. A companion gathers outside a line set by tides. Crust floats from melt. Incompatible elements pool. Earth's day slows while its nights gain a lamp. And somewhere between the certain and the permissible, a minor sibling waits a little while, then merges gently and is remembered only by a hemisphere thicker and brighter than its partner. Only took an hour of heat to write 4.5 billion years of shadow. Only took a ring of rock vapour to become a librarian of tides. Only took a loss of spin to purchase a partner that keeps the planet's seasons in a range where oceans can think. The birth of a singular moon proceeds without announcement, a steady untying of heat into stone as the glowing debris around Earth cools, stratifies and remembers how to be gravity. The ring born from the impact spreads like a low bright storm around the planet and beyond a certain invisible line, the Roche limit, where tides relent and clumps can hold. The fragments begin to stick first, as lumpy aggregates, then as rounded embryos that learn their own pull. In third person, present time becomes slow viscosity. Molten droplets share. Orbits collide at walking speeds, merge and soften their shapes. Vapour condenses as rain of silicate fog that settles toward the disk's mid-plane, making a murky river of melt and rock that moves angular momentum outward the way wind moves ripples along a lake. The scientific fact along the spine is plain and sufficient. The Roche limit fixes the inner boundary for accretion, and outside it the self-gravity of fragments can overcome tidal shear. Models show an inner tidally ground ring feeding an outer nursery conveyor that transfers mass in pulses so the principal moon grows from repeated arrivals, not one sudden casting. Under this slow hail, a primary clump takes precedence beyond roughly 3 Earth radii. Its hill sphere, its zone of influence, enlarges with each meal, and smaller neighbours become moons of a moon before folding into it. Accretional shocks radiate heat into space on the night side, and into the disk on the day side, the infant satellite glowing dimly in thermal infrared under an Earth that still smoulders red. A lesser-known detail passes soft as breath. The newborn moon's face, though airless, may wear thin ephemeral halos of vapour during heavy accretion. Nanobar atmospheres lofted by impact heating and surface sputtering fuzzy veils that collapse back to frost or escape to the void with every cooling. Nothing like this remains, but the physics permits a brief whisper of atmosphere in a place destined for vacuum. The geometry of growth keeps its modesty shepherding resonances in the disk, carve wakes, vortices, trail clumps, and the Tumarq parameter borrowed from the language of galaxies marks the line between clumping and smoothness. It stays just low enough to let gravity stitch the fabric. As mass swells, the proto-moon damps its own eccentricity through tides raised on Earth and tides raised upon itself, and the synchronous state beckons rotation slowed by torques until one hemisphere always faces the planet, a lock that will persist so long that the word far side becomes permanent. Beneath any temporary skin, the surface grades into a magma ocean hundreds of kilometers deep. Plagioclase crystals buoy up from the convecting melt like pale ice in scarlet soup and raft together into an orthositic crust. Denser pyroxene and olivine accumulate sink-stacking layers that will stiffen and wrinkle through 4 billion winters. Ilmenite-rich residues concentrate in pockets, and a last incompatible brew, creep huddles, in seams where later fractures will coax out basalt to flood nearside basins. A quiet scientific mystery keeps its seat at the table. How rapidly does the disk cool enough to let isotopes equilibrate between vapour and melt before being locked into solids? If the exchange is thorough and fast, Earth and Moon inherit nearly indistinguishable oxygen, titanium and tungsten signatures. If not, then Theia must have formed so near Earth's orbit that its isotopic accent already matched. Models allow both, and the rocks agree only that sameness wins not how it arrived. Earth above is no silent spectator. It spins short, perhaps 5 or 6 hours per day, drives tides as tall as continents in the newborn oceans of rock and steam. Tidal friction converts rotation into lunar distance, the moon inching outward with each cycle in a tray that can be measured eons later by lasers flicked off retroreflectors. The arithmetic is not poetic, but the result is the farther the companion moves, the longer Earth's days become, and time itself on the surface changes its stride. 3 soft ironies breathe through this quiet workshop. The collision that could have unmade Earth instead equips it with a stabilizing partner that will mellow obliquity and favor long habitable climates. The airless bead that looks least like Earth becomes by isotopes the solar system's most Earth-like object, and the very tides that threaten coasts today are the same mechanism that once lifted the moon away a benign theft of spin that bought a night lamp. The newborn satellite's orbit interacts with the remnant ring below the Roche limit. Gritty, tidally shredded rubble spirals inward to Earth, or is torqued outward, where the moonlet can sweep it up. Each intake arrives as a drizzle of impactors, not enough to melt the globe wholly again, but enough to keep the upper ocean hot and convecting. Cooling winds finally by radiation to a dark sky. Earthshine, ruddy fierce, slows, but still rivals sunlight on the lunar night side, and in that full stay the crust thickens unevenly. Locations with persistent heating lag locations in shadow-led. If the two-moon scenario is quietly true, the singular birth still owns the centre. The principal moon condenses and rounds, establishes lock and migrates outward. The smaller companion, if it exists, only reframes the far side later by plaster, not by authorship. In any case, the magma ocean's chronology proceeds feldspar rafts collide and orthosite plates weld, and the first highlands rise as the earliest crust Earth or Moon will ever make. A gentle modern analogy comes and goes, The disk behaves like a pot of sugared syrup settling toward a glassy state, while one large crystal grows at the rim and slowly incorporates smaller ones, a process whose patience is noisy only under a microscope. The infant moon's gravity soon becomes strong enough to gather a retinue pebbles boulders, mile-wide stragglers, while leaving the disk increasingly starved. The last of the inner ring falls back to Earth as luminous rain, and the outer nursery thins until only the big survivor remains. Mascon's dense mantle plugs beneath nascent basins lie in wait, not yet weighted by impacts they will later receive, but already the planet-satellite partnership begins to sketch a gravity field, whose quirks future spacecraft will need to learn if they are to orbit safely. Another lesser-known tactile detail hides in texture. As plagioclase floats, it traps bubbles, and the degassing of those bubbles can drive tiny fire fountain eruptions later in low gravity. Apollo glass beads preserve this behaviour as cooled globes, some nearly perfect spheres, each a crystallized breath from a fire that never needed air. The mechanics of the larger system remain serene. Conservation of angular momentum holds court. The lunar semi-major axis grows eccentricity damps, and the evection resonance with the Sun, if ever engaged in a high angular momentum variant, bleeds off the extra, whichever path the numbers pick. The present day's budget is met without melodrama, a ledger balanced by tides and time. 3 more soft ironies settle with the cooling crust. The moon that steadies Earth's seasons was born of a day so chaotic it would have defied seasons entirely. The oldest intact crust in the Earth-Moon system survives not on the larger world, but on the smaller one that never learned weather. And the more complete the birth becomes, the quieter the sky grows, until the event that made everything we now see leaves nothing moving fast enough for anyone to notice. A gentle uncertainty remains in the core. Does the moon preserve a small metallic centre, spun from Theia's leftovers and Earth's scattered drops? And how does that core, if present, reflect the early dynamo that some signatures hint once ran? Seismic hints from sparse stations suggest a partly molten boundary in modern times, but the Hadean blueprint is a palimpsest smudged by collisions. The question is tidy and patient, waiting for future arrays that can triangulate moonquakes with continental confidence. By the close of this long birth, the singular moon exists in all the ways that matter, a globe airless and bright, locked in face afloat, above an Earth whose days already lengthen. The disk that suckled it has thinned to arcs and then to memory. The Roche limit stands behind as an equation in a book rather than a visible ring in the sky. The magma ocean begins its climb toward a crust that will keep the sun's light in pale stone. And Earth for the first time carries a permanent companion able to reflect the next 4 billion years back, at any eyes that will someday look up. The section leaves the infant where it belongs, present cooled enough to crust, warm enough to convect, committed to a slow outward walk, while the planet below cools toward oceans and weather. No flourish arrives, only the steady kindness of physics. Clumps at the right distance glue into a body. Tides select a face to keep. Heat makes a skin. Spin leaks into distance. And night gains a keeper whose silence will outlast every story told beneath it. Only took a ring of bright rubble to become a single disciplined sphere. Only took the theft of a little spin to purchase stability for a world. Only took a hot hour and a cool million years to leave a lamp that does not tire. A second orb from the same fire is not announced with trumpets. It is proposed in the quiet language of simulations, a small worldlet gathering from the luminous ring, that the impact leaves a leftover clump that coalesces where tides permit, not far beyond the Roche limit and not far behind the principal moon. In third person present, debris cools, coarsens and clumps, and among those clumps one grows farther, slower, more modest, perhaps 1/30th the mass of the main moon, an attendant born of the same hot sheet of silicate vapour and melt. The scientific fact at the centre of this suggestion is simple enough to hold gently rings outside the Roche limit, can breed multiple embryos and co-orbital dynamics. Around a massive primary admits sanctuaries, the Trojan neighbourhoods, 60 degrees ahead, and behind the horseshoe loops that swap longitude softly, so that a smaller satellite can share the same broad path without immediate collision. perturbations from Earth's tides, and the sun's pull slowly work on those sanctuaries, turning long stability into transient refuge measured in millions, not billions of years. In such models, the small companion librates about a Trojan-like point, with period-length swings drifting ahead of the big moon and then falling behind while the principal satellite moves outward under tidal torques. The geometry reads as choreography, rather than chase two pale beads threaded on one moving path, their relative speed so low that night after night they keep each other in view. A lesser-known detail flickers politely at the margins of these equations in our own epoch. Earth keeps a handful of co-orbital asteroids horseshoe and quasi-satellite travellers like Kamoa-Lewa that prove the dynamical niche is real even for fragile sunlit stones. They are not moons, but they are a reminder that orbits echo with options and that shared year does not mean same place. The second orb persists in the simulations because tidal damping reduces relative speed, and because torques from the disk and from Earth conspire to hold it near the main moon's leading or trailing flank. Occasionally it slides into a near circular offset that resembles a miniature convoy. Occasionally it wanders farther and returns. In every case, time is the solvent that eventually undoes the arrangement, and the unravelling leads not to shrapnel, but to embrace. A quiet mystery sits in the middle and refuses to harden if such a companion forms. How massive can it be without forcing catastrophe? Models breathe numbers, fractions of the lunar mass radii of a few hundred kilometres, and choose relative velocities at approach of only a few hundreds of meters per second, enough to fuse without global melting. A big splat that thickens the far side with buoyant crustal material that behaves like pale plaster poured at walking speed. But the true mass speed and timing remain gentle unknowns, unpunished by data and unendorsed by them, and a loud story rather than a necessary one. Meanwhile, the main moon continues its slow outward walk, and Earth beneath it spins through short days that tides stretch little by little. Earthshine, fierce on lunar nights, paints both faces with ruddy light. In that glow, the small companion, if present, is not a star but a peach-tinted bead drifting near the larger disk's shoulder, a domestic detail that feels right even if no eye ever saw it. Two reflections travelling together in a sky lit by a hot planet. Three soft ironies drift with the pair the extra moon invoked to explain a symmetry survives only by approaching slowly enough to erase itself. The thickened far-side crust that best remembers its presence is the hemisphere no human on Earth can see, and the hypothesis that makes a second visible light in the imagined sky does so precisely to explain a feature discovered only by invisible gravity and silent orbital mapping. The mechanics that escort this second orb are neither exotic nor complacent. Lagrange points in the Earth-Moon frame are distorted by the Sun's pull, and co-orbital stability in a three-body problem under solar perturbations is a privilege lent, not a right. Resonant kicks from the Sun nudge the companion off its long libration, and tides raised on the small body by the main moon warm it and circularize its track, all while the semi-major axis of the larger satellite grows. The upshot is an approach along a shallow incline and a grazing merger that dumps light and orthositic material onto the far side, with a preference set by geometry and by buoyancy. A gentle analogy visits and leaves two icebergs drift in a slow wide current, the larger making the water around it calm, the smaller riding in that calm until a turn brings them together. They do not shatter, they simply kiss and stick, and the seam becomes part of the large flow's unknown underside. In rock language, the kiss would look like a farside cap thicker, an orthosite, deeper highlands, an enduring topographic plateau. This is compatible with modern gravity and topography. Grail maps that show a farside crust markedly thicker on average than the near side, and with the distribution of creep-rich basaltic infill that favours the near-side basins. It does not prove a second moon, but it makes space for it the way a coat hanging on a peg makes space in the mind for the wearer who might return. Another lesser-known tactile note whispers from Apollo's trove fragments of pure anorthosite light. Buoyant plagioclase rock record a flotation crust that is exactly the kind one expects from a global magma ocean. And those pieces show ages clustering early, a sign that the thick pale shell formed quickly and was not remade wholesale. A later plastering of more anorthosite on one hemisphere would fit that register by adding thickness, but not betraying itself in new chemistry, a quiet layering that keeps the isotopic sameness intact. The second orb's warmth is a modest bookkeeper of heat. Tidal dissipation inside a small body near the main moon is not nothing. It can make a warm rind soften fractures and permit ductile plastering, but it will never rival the vast energy that the primary's magma ocean already holds. And so the merger does not have to rewrite the moon, only to retouch a hemisphere that cooling has already made light and stiff. 3 further soft ironies pass like high clouds. The more carefully models find a gentle path to merger, the more plausible it becomes that no mark sharp enough for certainty would remain. The idea most attentive to thickness and topography asks the least of chemistry, so the very evidence that would convince most people is the evidence the hypothesis predicts will be muted. And in a public imagination stocked with catastrophic collisions, the event that would matter here is notable precisely for not being dramatic, an accretion at walking speed across a ridge older than continents. Uncertainties keep the posture even. Does solar evection and orbital resonance that can siphon angular momentum alter the pace of approach? Does the small companion sit ahead of the main moon and then fall back, or the reverse? What of inclination do nodal precessions tilt the plaster to longitudes that match specific fairside basins? How does a stiffening crust accept a gentle load without global cracking? Patient codes can vary these dials and make similar hemispheres. None violates physics, none binds truth. The quiet presence of alternatives keeps courtesy. Asymmetric tidal heating in a moon held early at closer distance could keep the near side warmer for longer, thinning its crust, while the far side thickens. Concentration of heat-producing elements creep on the near side could extend volcanism there and leave the far face more ancient and bright. A preponderance of giant impact striking the near side at later times could thin and fill, making basins and seas that accent the asymmetry without invoking a sibling. These scripts compete with grace because each is sober and sufficient, and the two-moon story lives beside them like an offered seat at a long table. A small real-world image helps the mind on some winter nights. The moon's dim outline is visible inside the crescent earthshine lighting the night side with a slate glow. In the imagined deep past of a hot earth, that earthshine is no slate but copper, bright enough to cast shadows, and in that false day a smaller pale companion would hang nearby, its phase echoing its outline a second punctuation mark in a sky, already crowded with the planet's own fire. The picture is accurate in physics and impossible in memory, and it is exactly the kind of image that this story tolerates quiet, plausible, and gently unprovable. Mechanics continue their slow kindness. The main moon remains tidally locked. Its outward migration lengthens days on the planet. The companion tightens its loop until a shallow collision adds thickness, where the far side is already light. When the seam cools, the second orb ceases to be an orb and becomes geography. Billions of years later, gravity maps read that geography with a sensitivity strong enough to notice invisible mountains of crust, and seismology waits for future arrays to sound for sutures beneath. The section ends with the understanding that nothing here needs flourish. The second orb is a permitted character that exits without line, leaving only a heavier hem on a pale cloak, and a suite of alternatives that can explain the same costume. The mystery remains welcome and unhurried. The moon above the window keeps one face, and the face we never see remains the most eloquent. The listener remembers 3 dry observations worth keeping. Only took a tiny patient world to make a hemisphere that looks inevitable. Only took the faintest embrace to leave the loudest asymmetry. Only took a second moon to become a thickness that has no moon in it at all. Orbits in uneasy harmony look calm from a distance. 2 small worlds, the larger and the lesser circle, a hot, fast-spinning Earth on slightly offset paths that share a year, but not a longitude, their separations breathing in slow librations, as tides tug shapes, phases, and speeds toward a future they do not yet know. In third person present, The geometry behaves like a whispered arrangement. Co-orbital corridors near Trojan longitudes, horseshoe arcs that trade places politely shallow inclinations that let the pair drift across one another's sky without touching. The scientific fact at the spine is spare and sufficient in the restricted three-body problem with solar perturbations. Bodies of unequal mass can occupy co-orbital niches for long intervals, lingering 60 degrees ahead or behind or sliding in broad horseshoes while tidal forces raised by Earth and by the main moon bleed energy and angular momentum, tightening or loosening loops until a gentle approach becomes likely. Stability is real, but lent not owned, and time in such sanctuaries is measured in millions, not billions of years. The lesser-known tactile detail folds in at human scale. The leading and trailing Trojan points are not points in practice, but fattened ponds of quasi-stability, and within them the smaller companion can librate with a period of centuries its sky position, as seen from the main moon wandering round a mean angle, while Earth's tides deal tiny talks that the numbers call love-number coupled, a phrase that belongs to textbooks, but reads like a note about how easily rock can be persuaded to bulge. Earth's rotation remains short days of perhaps 5 or 6 hours, and equilibrium tides are tall, because the tidal bulge on Earth is carried slightly ahead of the Moon by friction torque transfers rotational energy into lunar orbital energy. The larger satellite uses that gift to drift outward, and the smaller sharing almost the same semi-major axis feels the changing geometry as a slow, insistent wind pushing its co-orbital loop wider or narrower. In the same present tense, the main moon tends towards synchronous spin, while the small companion with its weaker gravity and different shape damps faster or slower, depending on interior heat and porosity. Synchronous states are attractors, and soon both worlds keep essentially the same face toward Earth, a quiet choreography in which the lesser orb hangs near the main moon's leading or trailing limb like a pale page marker, its phase echoing but not identical, because separation on the sky means different sunlight angles. A quiet mystery persists in the arithmetic as the pair evolve through an evection-like episode, an orbital resonance where the precession of the main moon's perigee matches Earth's motion around the Sun, altering eccentricity and bleeding angular momentum to the Sun, thereby adjusting how quickly the co-orbital corridor shrinks. Or do they bypass that door, entirely sailing on slower secular changes toward a meeting? Both routes solve both are polite, and geology is not yet sharp enough to pick. The larger frame, Sun-Earth 2 moons, writes slow modulations into the sky. Nodal precession tilts and untilts the pair's orbital plane with respect to Earth's equator. The Laplace plane transitions as the dominant torque shifts from Earth's oblateness to solar gravity. Obliquity of the main moon relaxes toward a Cassini state, in which its spin axis orbit normal, and the normal to the plane that balances torques remain coplanar. The smaller companion feels the same family of torques, scaled down its own Cassini-like alignment, a smaller echo in a field of larger echoes. 3 soft ironies move through this tidy ledger. The same tide that pulls the larger moon away from Earth makes the smaller one's relative distance to it fluctuate until closeness becomes irresistible. The shared orbit arrangement that looks stable from a single night's glance contains its own untying written only in slow angles. And the mechanism that appears to separate recession driven by torque is precisely the mechanism that arranges a meeting of neighbours who were safest when they were most apart. In the nights above, the hot planet Earthshine cast copper shadows. From the main moon's near side, the lesser companion often appears near the horizon, sliding with dignified slowness across a background where constellations shorten into streaks because the sky is mostly planet and glow. From the smaller orb, the main moon is a dominating disk whose gravity lifts tides in rock, a physical intimacy that deepens as libration brings them fractionally closer on some centuries and farther on others. The two bodies communicate through tides without speech storing and releasing energy as microscopic strains that instruments would one day be able to measure if instruments existed to be placed there, To the bookkeeper's eye, the paired motion answers clean equations. Co-orbital resonant angles evolve under weak dissipation. Libration amplitudes grow as the main moon's semi-major axis changes, and as the sun's perturbations stride in and out of tune. At some epochs, the smaller companion traces a horseshoe around the shared mean motion, approaching the main moon from behind, slowing, reversing and retreating only to repeat on the other side. At others, it sits near a Trojan angle and swings about it like a pendulum in slow air. In both cases, relative velocities at closest approach remain modest hundreds of meters per second. In many solutions, numbers compatible with a merger that thickens without pulverizing. A gentle analogy arrives and leaves two skaters on a slow-crowded rink move in wide loops that keep them apart by courtesy and by rules, yet friction on the ice, and the rink's gentle slope bring their paths nearer over an afternoon, until a soft touch transfers momentum and they glide as one. The rink here is space-time curved by Earth and touched by the sun, and the friction is the whispered work of tides. A lesser-known observational sibling in today's sky offers proof of concept rather than proof of history. Earth keeps quasi-satellites like Kamawalewa that share the year with us in loops that, when plotted from the right frame, look like bound companionship. They are not moons, but they demonstrate that co-orbital choreography is a real possibility that gravity permits even in a noisy solar system, and that long-lived sharing of a broad path does not ask for myth to sponsor it. The pair's harmony is uneasy because small differences compound the main moon's mass dominates the local gravity field, carving tadpole-shaped libration zones. Solar tides slowly reshape the allowed regions. Tidal dissipation within the smaller companion rounds its figure, lowering moments of inertia and changing its spin state until torques from the main moon and Earth pass energy back and forth in new ratios. The result is a very slow drift in the companion's guiding centre that no eye could notice but all futures will honour. A factual aside, gentle and exact, adds a modern measure. Today the moon recedes at roughly 3.8 centimetres per year, known from laser ranging to corner reflectors placed by astronauts. In the early hot epoch, the rate is far larger when Earth's oceans are not yet settled and dissipation is more efficient. The consequence for this scene is simple. The outward march is fast compared to later ages, and what appears eternal in one frame is a brief phase in another. 3 more soft ironies pass like high clouds on a still night. The configuration most likely to let 2 moons survive for a while is also the configuration most likely to make them rendezvous gently in the end. The part of the moon that will carry the louder geological memory of such an age is precisely the hemisphere that never faces Earth, so the clue is hidden by the very synchronous lock that tides insist upon, and the cleaner the equations appear on paper, the more they admit families of outcomes, merger, escape, long co-orbital dance, none of which the rocks are obligated to select for our satisfaction. The larger system, the sun's year wrapped around Earth's day, sets pacemakers in the problem. When the precession frequencies of the pair's orbits resonate with the sun's apparent motion, arguments of pericenter can freeze or flip, eccentricities can pump, and then damp inclinations can be traded for heat through tidal dissipation. If the smaller companion's inclination grows mutual, encounters occur slightly out of planies in the approach into a graze rather than a head-on event. If its eccentricity grows pericenter, passages near the main moon become fertile ground for capture, into a bound low-velocity loop that collapses toward contact. A quieter poetic detail lives in light on the molten Earth below the pattern of tides from 2 moons beating near, but not identical frequencies, writes a subtle interference, a slow amplitude modulation that would move coastlines of magma by meters on long timescales. No witness to feel it, yet an honest rhythm that would have existed because the sums say so. The mystery that stays polite is whether the co-orbital interval lasts long enough to leave structural fingerprints distinguishable from other causes. Far-side crustal thickness differences, mascon distributions and heat flow asymmetries all obey alternative scripts: early tidal heating, asymmetry, uneven, creep concentration bombardment, so the harmony here might be real and yet become indistinguishable in stone from harmonies written by other instruments. The hypothesis is allowed but not required, which is the right temperature for an idea in a calm story. The section lingers briefly on the concept of internal tides. The main moon's gravity needs the smaller companion dissipating energy as heat that softens lithosphere and lowers yield strength. That softness makes ductile plastering at eventual contact more plausible than brittle failure. The same kneading mirrored at lower amplitude the other way adds a touch of warmth to the main moon's outer layers, an influence tiny compared to Earth's yet non-zero, another thread in a web that is mostly woven by the planet and the sun. By the time this uneasy harmony has aged through its allotted quiet, the outcome is set by angles and patience. The smaller companion slides into a corridor where relative speed is low. The main moon's leading limb becomes a coast. The touch that follows is not a catastrophe but a redistribution. The co-orbital niche empties. The pair becomes one, and the harmony ends by resolving into a single note that will ring for billions of years. The present tense telling stops before that meeting. It keeps the two orbs circling under slow, exact laws, visible to each other across a few lunar diameters, committed to corridors that geometry permits and tides edit. No flourish arrives, only 3 soft, dry observations worth keeping. Only took shared longitudes and unequal masses to make a duet that cannot last. Only took the same talk that buys distance to fund closeness. Only took the calmest arrangement, a shared path to lay the quiet rails toward a gentle collision that will leave its memory where no one on Earth can look. The slow dance toward collision unfolds without spectacle, a geometry written in long patience as the smaller companion drifts on a co-orbital leash that tightens by increments too fine for any witness. In third person, present both bodies orbit a cooling Earth while tides in mantle and crust raised by Earth's sun and each other rearrange small stores of angular momentum into large decisions about approach, and the numbers that govern this choreography libration amplitudes around Trojan-like longitudes, precession rates of nodes and periapsides, tidal quality factors and love numbers quietly step together until relative velocity relaxes toward a few hundreds of meters per second, a speed that prefers embrace to shattering. The scientific fact anchoring the scene is sober and narrow. Tidal dissipation transfers rotational energy from Earth to the orbit of the main moon driving recession, while weak dissipation within the satellites themselves damps eccentricities and inclinations. The co-orbital configuration stable on million-year windows but not on billion-year ledgers evolves through solar perturbations and secular resonances so that the smaller companion's guiding center shifts its horseshoe loop or tadpole swing, shrinking until close passages occur at low speed and small angle, a condition compatible with gentle accretion, rather than catastrophic impact. The path to that condition is a ledger of small terms that grow persuasive together. Evection-like episodes bleed angular momentum to the sun when the main moon's perigee precession locks to the year. Nodal precession buffeted by the transition from Earth's oblateness to solar torque as the moon recedes, tips the orbital plane enough that approach vectors arrive slightly off-plane, reducing impact energy. The Cassini state settling of the main moon's spin axis aligns internal tides to external torques and simplifies the long beat of heating and cooling. In the lesser body, tidal flexure warms and softens the lithosphere, until ductile behavior is plausible at a shallow crust, making any future contact a press and spread rather than a crack and scatter. A lesser-known tactile detail rides under the arithmetic like fine print. At very close distance, the main moon's gravity can capture the smaller companion temporarily in a low eccentricity, low inclination loop, a brief binary state with hill-sphere scale measured in a few thousand kilometers, so that the last approach is not a plunge from infinity, but a few slow turns in the same neighborhood, a choreography that lengthens contact time and favors a blanket of buoyant crust piling onto the far side rather than vaporizing into a global spray. Earth below, still losing spin to tides, lengthens its day by heartbeats over centuries. Each extension subtly revises the resonance map that the pair must cross, moving the exits and entries of corridors in phase space, the way a shoreline redraws itself with a falling tide. The smaller companion continues to circulate near the main moon's leading or trailing limb, its orbital elements gently pumped by solar tides and then soothed by internal dissipation, and the result is a long drift of relative longitudes toward a state in which the difference becomes not a gulf but a seam. A quiet scientific mystery keeps the tone even, which resonance does most of the work. Evection with the sun evictions from Trojan ponds, by subtle three-body terms, or slow tidal drift across a landscape of weak commensurabilities, and does the smaller body approach from ahead or from behind? Models admit families of paths each permitted by mechanics, and stone on the ground does not yet discriminate among them tightly enough to name a victor. The uncertainty is not a flaw, but the atmosphere in which this calm story breathes. The pair's mutual tides speak through stress and heat rather than sound. The main moon's tidal field needs the lesser companion with amplitudes that fall, as the cube of distance a strong grammar when they are within a few lunar diameters. Viscoelastic response converts periodic strain to thermal comfort in the smaller world. Lets outer crust, lowering yield strengths, so the northerzitic rafts and brecciated regolith products of earlier cooling and small bombardment can deform without explosively fracturing when a shoreline of rock meets a shoreline of rock. The larger body reciprocates with fainter internal tides, a murmur of warmth too small to change destiny, but enough to keep the outer kilometers more patient than they would be in a perfect crystal. 3 soft ironies pass like faint shadow across frost, the very process that separates the main moon from Earth. The tidal torque that funds recession brings the smaller companion closer to the main moon by shrinking their relative phase and velocity. The configuration whose serenity suggests permanence. 2 satellites sharing a path turns out to be the arrangement most likely to arrange an ending. And the hemisphere that will carry the loudest record of the meeting is the face that Earth never sees, a reminder that the sky keeps its brightest explanations just out of view. In the long approach, solar geometry participates as a courteous editor. When the angle of sunlight relative to the pair's line of centers favours cooling on one flank and warming on the other, diurnal thermal stresses add tiny torques on shapes that are not perfect spheres, torques that integrated over millions of orbits, nudge spin rates and thus tidal response. The cumulative effect is not dramatic, but it is the difference between a collision that happens a little sooner, at a little shallower angle, and one that waits a million more summers to arrive from slightly above or below the plane. A gentle modern analogy comes and goes. 2 weathered barges in a broad, slow river drift side by side for a very long reach, eddies and faint winds turning them by degrees until their bumpers touch with patience, and remain not because any captain aimed for it, but because the river, the wind and the tyres all prefer contact to gap once spacing falls below a certain width. In the formal ledger, the last tens of thousands of kilometres are an exercise in reduced relative kinetic energy. The smaller companion's true anomaly at encounter aligns, so that velocity at infinity is nearly zero. Gravitational focusing by the main moon bends the path into a capture-like loop. Tidal dissipation during that loop damps oscillations and collapses the orbit in a few revolutions. Contact spreads over minutes to hours, along a track that crosses the far side at highlands, latitudes rather than near-mare basins, in harmony with the long-standing thickness contrast that modern gravity mapping reads like braille through a glove. Another lesser-known detail that fits politely without insisting. If the small companion carries a colder core or a higher porosity mantle, its bulk density could be slightly lower than the primary's outer crust. Buoyancy would then favour its material plastering high, and remaining high a geologic frosting that deepens the far side's northositic plateau, without delivering much heat to the near side where mare basalt later pools from internal reservoirs enriched in heat-producing elements. Chemistry stays almost unchanged, topology changes. The hypothesis asks for geometry, not exotic minerals. The numbers give the quiet collisional requirement its margin a few hundred meters per second, relative speed grazing angle ductile outer layers. This is not a demand for luck so much as a consequence of co-orbital drift and tidal damping in a system that spends millions of years making sure most fast options have already been ruled out. If the speed is higher shattering and global melting, follow leaving a moon we do not see. If lower, the companion might be ground down into a chain of rubble that still accumulates on the far side ridge first. In either case, the expected asymmetry in thickness remains a stable outcome of many gentle paths, which is why the story can remain humble and still be plausible. 3 further soft ironies step down quietly. The gentlest collision in the early solar system, gentle by the standards of worlds, could be the one that leaves the most obvious hemispheric signature. The most natural time to look for the proof now with orbiters and maps coincides with the least direct evidence possible, because chemistry and isotopes do not help much when 2 bodies share a parentage. And the strongest demonstrations that such low-speed contacts can happen come not from the moon at all, but from small current co-orbitals and quasi-satellites in Earth's neighbourhood analogies that prove possibility while refusing to certify history. Through the last passages, the main moon's synchronous lock ensures that Earth remains in the same skyward direction, and so the seam that results from contact inherits a permanent orientation. The far side acquires thickness that resists later erosion and later mare flooding, while the near side favouring heat and thin crust becomes the basin field that will one day fill with basalt seas. The asymmetry that telescopes read in shadow becomes a memory trace of a slow dance. No eye ever watched, consistent with alternatives, tidal heating, asymmetry, creep concentration impact distributions, yet uniquely comfortable with the notion of a partner that disappears into thickness. The approach completes its grammar with one more line once contact is made and the small companion's mass spreads. The system loses the co-orbital term forever. There is no niche left to refill, no second embryo waiting in the wings. Recession resumes as a one-body problem. Earth's day continues to lengthen. The seam cools and grows stiff. Later impacts scratch across it without revealing what lies beneath. Seismology, if it one day grids the far side with stations, may hear density contrasts that betray sutures at depth. Until then, gravity maps remain the quiet readers of the thick pages we cannot turn. The section ends where the dance most nearly touches hand to hand but does not yet clasp. It holds the approach as a present tense convergence, an arithmetic that transforms shared longitudes into a single geography and leaves 3 dry observations floating like dust in weak gravity. Only took a million small talks to trade distance for a seam. Only took the slowest kind of collision to leave the largest quiet difference. Only took a partner to vanish so the moon we know could keep one face thicker and brighter than the other. The gentle accretion hypothesis sits down in the cool of the far side and speaks in low numbers rather than declarations. In third-person present, the smaller companion approaches the larger moon at a pace that does not require shock to explain rock a few hundreds of meters per second at most, a graze that prefers spreading to shattering a press that thickens the quiet hemisphere that never faces Earth. The scientific fact at the centre is modest and clear. Modern gravity and topography reveal a far-side crust markedly thicker on average than the near side, while creep-rich materials and most broadmare basalts concentrate on the near side. A paired asymmetry in thickness and heat sources, consistent with but not compelled by a slow merger that adds buoyant and orthosite to one face and leaves the other hot enough to flood with basalt later. In this telling, the lesser body arrives as a pale cool quilt, its anorthositic crust floating, because plagioclase remains lighter than underlying melts. Tidal flexure and internal warmth make the outer kilometres behave ductilely, so the contact is a long hush of rock behaving like very cold wax smearing across highlands where crust is already light. The seam does not announce itself, it settles. A lesser-known tactile detail comes forward. Orthosite, the feldspar-rich rock that composes much of the highlands, forms from flotation in a magma ocean. Its grains interlock like tight ice. and when warm enough to yield but not melt, it can creep along centimetre by centimetre under sustained stress. This is the kind of motion the hypothesis asks for at contact. No global vapour cloud, no hemispheric pond of melt. Only the slow, obedient rearrangement of buoyant stone under a gravity not quite strong enough to insist on collapse. The small worldlet presses, the plateau grows, and the far side's bright crust thickens by tens of kilometres in models that give the companion a few percent of the moon's mass. The exact figure is unneeded in this room, only the sense that the thickness difference now observed does not embarrass the idea. A quiet scientific mystery keeps the tone even if such a plastering occurs. What becomes of the lesser body's deeper layers do denser cumulates, and any small iron core sink through the contact and vanish into the primary's mantle. Are there buried lobate scarps or density contrasts that later seismology could hear as echo? The far side lacks a vintage network of seismometers, so the interior keeps its vote secret. Gravity data read the surface pages. The spine is still closed. The flow of this low-speed meeting writes itself into a geography that telescopes already know highlands, with fewer Maria basins that do not flood as readily, because thickness resists a hemisphere that keeps its brightness, because basalt stays mostly on the other side. In this, the hypothesis allies with thermal logic. If the near side retains more Carite potassium, rare earths, phosphorus and heat producers, its crust stays thinner and warmer, preferring later volcanism, while the far side takes the weight and cools into endurance. The partnership divides labour between heat and height. 3 soft ironies drift like faint shadows over pale ridges. The second moon that would explain the far side is remembered most strongly when no one on Earth can see it. The collision invoked to account for asymmetry works precisely because it is too slow to make spectacle, and the hypothesis that adds a moon to history leaves the present with only one thickening geography until the extra body becomes indistinguishable from terrain. The approach geometry helps. Relative inclination lowers by tidal damping and secular precession, and so the touch slides rather than pierces. Gravitational focusing bends the smaller companion into a short capture-like loop that lengthens contact from seconds to minutes or hours. Each kilometre of track is a chance for crustal rafts to stack for seams to anneal under latent heat, for the downslope of early topography to accept a new higher baseline. Where the seam would prefer to crack ductile layers into seed, where the pile would prefer to slump low, gravity keeps angles of repose generous. The result is a far side that inherits heightened thickness without the near side's appetite for melt. A gentle analogy comes and goes. It is as if a slow glacier of bright stone slides up onto the rim of a continent and freezes in place, leaving the shoreline farther out with no ripple larger than a dune to testify that movement once filled that quiet. The hypothesis does not demand exotic chemistry. Both bodies carry the same isotopic accent because they share the same hot nursery. That sameness which once troubled early versions of the giant impact story now comforts this one. There is no need to hide foreign signatures in the far side, because there are none to hide only thicker layers of the same pale rock that already floats. A lesser-known observational whisper strengthens the mood. Grail's gravity maps reveal not just thickness, but also the far side's relative scarcity of dense mascons beneath large basins. If a plastering occurs early before the heaviest basins form, the far side's stiff, thick crust resists the degree of mantle upwelling that later helps to fix mascons beneath near-side Maria. The two effects, plaster and heat asymmetry, become partners rather than rivals, each reinforcing the other's map. A quiet uncertainty remains about timing. Does the merger arrive while the magma ocean still floats, plagioclase amplifying thickness as the flotational crust merges with newly landed anorthosite, or does it arrive slightly later when the crust is firm but warm enough to creep? Each schedule leaves a different thermal scar that only dense seismic arrays and subtle gravity inversions could hope to distinguish, and those instruments wait in future engineering. 3 more soft ironies settle like dew. The far side's greatest clue to a second moon may only be audible to instruments not yet built. The best time to have read the seam when it was still warm enough to outline itself was billions of years ago, before anyone existed to bring a notebook. And the hemisphere that holds the quietest, oldest crust is the one that took the latest gentle blow in this narrative, so the place most resistant to change becomes the place last altered. The reader of Rocks remembers that alternatives are honest. A moon held closer to Earth early on can suffer asymmetric tidal heating that thickens one face and thins the other without a companion. An uneven distribution of Kureep can lengthen nearside volcanism even without plaster. Large impacts can excavate and refill more on one hemisphere by chance. In this company, the gentle accretion stands simply as an allowed path that satisfies many constraints with one added motion. Its virtue is economy. Its limitation is that economy leaves few bold signatures. A lesser-known human-scale detail links idea to touch Apollo samples include pristine anorthosites, whose ages cluster in the first few 100 million years of lunar time. Their chemistry is consistent across sites and missions, a sameness that a plaster could preserve by adding more of what already floats. To a laboratory eye, the Farside's extra thickness need not announce a new ingredient, only an extra ladle dipped from the same melt. In maps, the Farside's highlands rise like a continent that never learned to see. Near its limb, as seen from Earth, the boundary between bright plateau and limward spill of craters carries no colour that reveals a seam, and that is exactly what the hypothesis expects. The seam is thickness, not pigment. If a signature exists, it may be a long-buried undulation in density, a S-shaped echo beneath a continental crust of another world. The scientific fact that frames humility near the end of this section is simple data do not yet isolate a sutured rim beneath the highlands. They agree on thickness differences and heat source asymmetries. They suggest histories consistent with gentle plastering and with its alternatives. The debate stays honest because the stones keep their secrets at the depth where certainty would live. Even so, a calm utility emerges from the exercise. The gentle accretion lens warns against overreading surface contrasts and invites attention to subsurface structure. It explains why Farside Maria are scarce without insisting they be absent. It suggests why nearside basins fill deeply, while farside basins often do not, and it keeps chemistry quiet while letting mechanics do most of the talking. 3 soft final ironies drift through before the lamp dims the hypothesis that could make the most romantic sky a brief age of 2 moons produces the least dramatic rocks. The stellar precision of gravity mapping that makes the idea plausible arrived only after the era of heroic exploration that brought stones home. And the strongest reason to consider a vanished companion is the enduring silence of the far side, its refusal to answer with lava, where the near side sings in seas. The section rests the idea without verdict. In present tense, the seam cools, the plateau keeps its height, the near side prepares its furnaces, and the moon resumes a single synchronized life. The small companion, if it ever existed, is gone without a grave, and what remains is a hemisphere that tips pale through darkness thicker by a story that may be true and useful, even if it is never proven in the way some minds prefer. Only took a few 100 meters per second to trade a moon for a mountain. Only took buoyant feldspar to turn collision into brightness. Only took an unseen seam to make a hemisphere that keeps its silence longer than any theory that tries to name it. Farside highlands, nearside seas, this pairing becomes a lantern. The moon holds steady and in third person present, the contrast reads like topography. Reciting its own sentences, the far side stands pale and mountainous, an orthositic crust, thick by tens of kilometers over planetary average, while the near side wears broad, dark basaltic maria that fill giant basins in layers hundreds of meters to kilometers deep. The scientific fact is simple and central. Global gravity and topography from orbit show the crust on the far side markedly thicker on average than the near side, a difference that helps explain why lava eruptions later in lunar time flood one hemisphere and mostly spare the other. In the cool ledger of maps, the far side's brightness is not paint but mineralogy. plagioclase-rich anorthosite floats early from a global magma ocean, coalescing into a buoyant shell that endures. On the near side, where heat lingers longer, crust thins under repeated melting and intrusion, making low spots capable of receiving basalt. The maria that later darkened the lunar face are simply the surfaces of old seas of rock that rose from depth and spread smooth, then took craters as a quiet rain. The far side, thick and cold, resists such seas and keeps its highlands. A lesser-known detail steps forward softly from those maps. Beneath many near-side basins lie mascons, mass concentrations, dense mantle materials upwelled and frozen beneath the mare plains. Gravitational anomalies so strong they once perturbed spacecraft into unstable orbits, until navigators learned the moon's interior punctuation. Far-side basins, by contrast, tend to lack equally strong mascons, a difference that mirrors the thicker crust and reduced mantle uplift on that hemisphere, as if the far side's shell holds the mantle at arm's length while the near side lets it touch. The chemistry that warms this picture is named without flourish. Creep potassium, rare earths, phosphorus, and heat-producing elements clusters in a province on the near side, known to cartographers as procellarum and imbrium surroundings. These incompatible components collect late from a shrinking magma. Ocean become trapped in pockets and elevate radiogenic heat locally. The near side thus carries more warmth for longer and accepts melt more readily, while the far side grows older, paler, thicker, and more reluctant to yield. A quiet scientific mystery keeps the tone even. Why did creep gather primarily on the near side in the first place? One path suggests early thermal asymmetry driven by Earth's fierce earthshine on a close newborn moon, keeping the near side warmer and modifying crystallization and convection. Another appeals to impact history, or to the inherited pattern of cumulates and overturn in the magma ocean. A third invites the gentle accretion idea, in which a slow plastering of anorthosite on the far side raises the lid and leaves the near side the natural home of late melt. Each is polite, and the stones answer only with partial hints. The largest basin of all, the South Pole Aitken Basin on the far side, adds scale without contradiction. A depression some 2,500 kilometres wide and more than 8 kilometres deep. It records one of the earliest and most energetic blows to the moon. Yet even there widespread, maria do not pour, as if the deep wound still meets a lid strong enough to hold back global flooding. A few localized basalt patches occur in small far-side basins, proof that volcanism is possible everywhere given a fracture and a source. But the broad seas stay faithful to the near face, a geographical bias written by thickness and by heat. Three soft ironies drift like high cirrus over this relief. The hemisphere Earth never sees in full is the one that keeps the thickest record of the moon's earliest crust, so the easiest surface to look at is the hardest to generalize from. The half that seems most varied to human eyes. The near side, with its myriad shapes and familiar features, is in many ways the simpler thermal story, a long tendency to melt and fill, while the far side's uniform brightness hides the more complex tectonic inheritance of extra thickness. And the strongest gravitational signatures that once threatened to pull spacecraft off course are the very clues that make the interior legible, so navigation becomes geology by necessity. In the near side's dark plains, mare basalts range in age mostly from about 3.9 to 3, 1 billion years, tapering off to younger flows in places. Their iron and titanium-rich compositions vary from basin to basin, telling of mantle source regions that were tapped in different ways and at different times. The far side highlands preserve older anorthosite and breccias with fewer smaller mare patches, their surfaces pocked and bright, a library of impacts written on pages that never learn to blacken broadly. A gentle analogy lifts and sets. The moon is a two-room house, with one room warmed by a small stove that never quite goes out, floorboards thin and occasionally replaced, and another room older and colder, its floor too thick to accept the same repairs. Open the door between them, and the warm air favours one side by architecture alone. A lesser-known tactile detail from seismic and gravity experiments complements the map's Apollo seismometers on the near-side recorded moonquakes that include shallow events thought to relate to tectonic adjustments as the moon cools and shrinks. Wrinkle ridges in the Maria and Labate scarps in Highlands confirm this global contraction, but their distribution and sharpness differ by hemisphere. The far side's extra thickness may distribute strain more widely, reducing the expression of some features while preserving others, another small note in the asymmetry's harmony. The discussion remains present and exact. Tidal heating early in the moon's history favours the hemisphere facing Earth, if the satellite orbits close because internal deformation aligns with the tidal bulge. As recession proceeds and the bulge weakens, this effect subsides. Yet its early influence on crustal thinning and mantle warming could have set the stage for later volcanism to prefer the near side. Combined with creep concentrations, this makes a layered explanation heat. Priming, then heat sustaining, while thickness on the far side stays in the way. Three more soft ironies move through the ledger, the basins most iconic to human culture: Mare Imbrium, Mare Tranquillitatis Oceanus, Procellarum are the youngest large features in the story, and tell the least about the moon's earlier structure, yet they dominate our casual memory. The far side rarely seen guards the oldest crust and thus the earliest chapter, but yields fewer photographs anyone frames. And the pattern? People learn to draw for fun. The face in the moon sees owes its existence to interior chemistry that no naked eye can see. So our most familiar map is 3 layers of physics deeper than its appearance. The Procellarum creep. Terrain, that nearside province rich in heat-producing elements, and late residual melt becomes a quiet cornerstone. Its gravity signature, geochemical hints from orbit, and coincidence with the densest mare population suggest a long-lived thermal anomaly. Whether that anomaly begins as a compositional quirk of magma ocean crystallization or as a structural response to impacts and mantle, overturn remains unsettled. In either case, it acts as a furnace that keeps near-side basins active and lowers the barrier to eruption, while the far side has to work harder for every flow. A quiet uncertainty threads through impact chronology, the late heavy bombardment once posited as a spike around 3. 9 billion years ago now reads more like a tale of declining impacts, or a cluster of events with complex cadence. Whichever cadence is chosen, basin formation on both hemispheres interacts with the thermal picture. Basins excavate crust, elevate mantle, and provide fractures. On the near side, those conditions plus heat make seas. On the far side, similar blows often leave rings and central peaks, without the same dark aftermath, another vote cast by thickness. A lesser-known observation adds a small domestic texture. Faint localized mare patches on the far side, like those in the Moscoviense basin, carry basalt chemistry that rhymes with near-side flows, but in modest volumes a reminder that the interior does not recognize hemispheres as rules, only as energy thresholds. Given the right conduit, even the thick lid yields, but it yields sparingly punctually, never with the broad floods that carve a face for cultures to recognize. The meditative ledger attends to present tools. Gravity inversions from missions translate orbital perturbations into crustal thickness. Estimates, while spectral imaging maps iron, titanium and maturity. Radar probes the shallow subsurface of Maria to estimate flow thickness. Laser altimetry traces the basin's precise rims. Each instrument adds confidence to the asymmetry without closing the debate on first causes. Future fairside seismology would matter most capable of triangulating deep reflectors to test for sutures, plumes long-cooled or compositional boundaries that prefer one hemisphere. Until then, the far side remains a page partly read through a light held from Earth. 3 final soft ironies settle before the section glides onward. The best evidence for why one side is dark and one side bright comes from instruments that never see either side with human eyes, turning invisible accelerations and spectra into maps more trusted than photographs. The hemisphere that feels empty of seas is the one fullest of early crust, so absence becomes presence when seen as thickness. and the very stability that lets the moon keep one face toward Earth ensures that the explanation for that face's difference is hidden on the other, so synchronous lock both presents and conceals the answer. The narrative keeps its even breath-far-side highlands stand as a durable monument to flotation crust and perhaps gentle plaster. Nearside seas record plumbing favoured by heat and thin lids. Mascons testify to dense roots beneath dark plains. Creep's quiet warmth helps time the eruptions. Earth's early tidal pull shapes the initial asymmetry. Impact sketch basins for molten ink to fill where physics allows. None of these lines contradicts the others, and together they write a geography that is not an argument but a balance. One hemisphere old and thick, the other younger in the large strokes, and both turning one face forever to the planet that gave the first heat and keeps the long rhythm of retreat. Only took a surplus of heat to ink oceans on one side and leave mountains on the other. Only took a lid a little thicker to spare a hemisphere from seas. Only took gravity's quiet preference written in mascons and maps to turn a two-tone disk into a record anyone can read in the dark. Clues hidden in lunar chemistry speak softly and persist, and in third-person present the moon becomes a ledger of ratios and traces written in stone and glass in bubbles, caught within beads in atoms that choose one mass number over another. The scientific fact at the spine is steady and puzzling in equal measure. Lunar rocks share almost indistinguishable oxygen, isotopic ratios with Earth's mantle D17, so close that the two bodies read as one reservoir, and their titanium, chromium and tungsten isotopes largely rhyme as well, a sameness that capture theories cannot support, and that giant impact scenarios must honour by invoking thorough mixing, or a Theia born near Earth's orbit. Apollo basalts, ferroan, anorthosites, norites, troctolites, and the delicate volcanic glass beads poured from ancient fire fountains all carry that shared accent. In the beads, tiny vacuoles trap volatiles once thought absent, and within apatite crystals and melting clusions, the moon whispers of water, tens to hundreds of parts per million in some cases, alongside fluorine, chlorine, sulfur and phosphorus. It is not a wet world, but it is not the perfect dryness once imagined, and the revision is quiet rather than dramatic. A shift from none to little that changes origin stories more than it changes landscapes. A lesser-known tactile detail glows in the lab light when lunar glass beads are heated gently in vacuum. They exhale minute quantities of H2O and CO, a breath measured with instruments that hear monolayers. This laboratory sigh echoes an ancient exhalation from erupting vents under 1/6 gravity. Each bead once arcing ballistically through black air, and cooling into a sphere whose chemistry became a time capsule. In those capsules, water's deuterium to hydrogen DH ratios vary, hinting at multiple sources' internal solar wind implantation, and perhaps inherited nebular components all braided into a melt that froze so fast it forgot to homogenize. The quiet scientific mystery is familiar but not tiresome. How does a moon forged in heat retain any volatiles at all? And why do some isotopic systems match Earth with uncanny precision, while others potassium's heavy isotopes, zinc isotopes, moderately volatile elements in general tilt toward depletion and fractionation consistent with loss? Models answer with synestias and hot disks where vapour and melt equilibrate before condensation, with turbulent stirring that erases regional accents with selective escape, that removes the lightest species while heavier ones condense back, but the exact intensity and duration of these processes remain parameters that patient papers adjust rather than facts that stone declares. In tungsten 182, a chronometer built from the decay of hafnium-182, with a half-life of about 9 million years, the Moon and Earth again nearly match, implying early and similar metal-silicate separations. Yet slight differences exist in some samples, and are debated without haste. Did late accretion of chondritic veneer smear signatures? Did equilibration in a vaporous shroud blur them? Did initial heterogeneities in Theia and Earth average away? Each answer is permitted and none is demanded, which is the safe temperature at which this story travels. 3 soft ironies drift like slow dust motes across the petrology bench, the rock that looks most alien under a small telescope. Pale, airless cratered carries a chemical accent most like Earth when measured precisely. The discovery that made headlines by finding water on the moon mostly revealed amounts so slight that they matter to history more than to thirst. And the isotopic sameness that strengthens the giant impact origin complicates the most cinematic versions of that impact by forcing the collision to stir rock into vapour and back with elegance rather than smash distinct ingredients into an untidy blend. In the near-surface environment, the moon maintains an exosphere instead of an atmosphere. Helium from the solar wind argon-40, from the radiogenic decay of potassium-40 in the crust. Neon sodium and potassium atoms sputtered from regolith, their densities so low that molecules rarely meet. When night falls and ground cools argon, 40's partial pressure changes and surface-bound volatiles migrate to cold traps, a daily tide of atoms without waves. In permanently shadowed regions near the poles, water ice accumulates over eons at temperatures cold enough to keep nitrogen hard and oxygen quiet. A scientific fact read by neutron spectrometers and radar, as a brightness that is really absence of hydrogen's hungry neutrons and a shine that is really smoothness on signal. This polar frost tells a second later story of delivery by comets and asteroids of solar wind OH, made on grains and driven poleward of a cold pantry that never existed when the magma ocean was young. The gentle analogy that helps here is a library one. The moon is a stack of books from different centuries shelved without labels, and chemistry is the trained hand that recognises typefaces. The earliest volumes, the Ferroan and Orthosite crust, and the cumulate mantles use the same type as Earth's mantle on their title pages, while marginal notes in potassium and zinc show pages torn and mended, and later pamphlets, polar volatiles, solar wind hydrogen, are slipped between boards that once were hot enough to char. Reading requires care, and contradictions are solved by assigning additions rather than tearing out leaves. In mare basalts, iron and titanium vary with source region. High tie basalts rich in ilmenite record mantle portions that collected dense titanium-bearing cumulates and then melted under pressure, while low tie basalts melt from sources less burdened by those layers. Thorium and uranium enrichments cluster on the near side where the Prosolarum creep terrain keeps its furnace. Heat-producing elements settle, their melts rise there, and the chemistry of near-side plains becomes both a map and a clock, announcing a thermal engine that ran longer and warmer on one hemisphere. Yet here the two-moon idea stays relevant without insisting. If the far side gains extra anorthosite by gentle plaster, it raises a lid whose chemistry matches existing crust, and thus hides itself in sameness. If the near side concentrates, Carib, it enriches melts that feed Maria, and makes a different chemistry that still speaks Earth's isotopic dialect. Either way, the bulk similarity of oxygen and titanium with Earth remains a spine that alternatives must keep, and the plaster story becomes a geometric amendment rather than a chemical revision. 3 more soft ironies cross the page. The isotopic signals that most strongly tie the moon to Earth oxygen and titanium are the ones least persuasive to anyone looking for visible difference, so chemical certainty arrives as sameness. The volatile depletions most compatible with high-temperature birth are recorded in rocks, dug and carried by hands that left footprints beside flags. Yet those rocks also whispered that the moon never forgot water entirely, undercutting the romance of absolute dryness. And the exosphere that seems emptiest offers the quickest daily weather. The moon knows proof that motion exists where almost nothing moves. A quieter, lesser-known detail sits in argon again. 40R36R ratios measured at different local times change because radiogenic argon escapes from warm regolith at night and collapses back into cold traps before dawn, a clock with a breath. On longer scales, the global abundance of argon-40 hints at potassium's distribution and thus at heat production, and here the chemistry leans back toward geophysics because heat shapes crustal thickness, and thickness shapes seas and seas, pattern faces that cultural stories recognise before chemistry ever calls them by name. In the oldest terrestrial zircons and in lunar zircons found within breccias, uranium-lead ages cluster at times when magma moved and cooled. Lunar zircons, small and stubborn, carry ages above 4 billion years, for some grains proof that crust existed to host them, and that the magma ocean's tail end met solidification on a schedule that fits models, with both rapid flotation of an orthosite and a drawn-out residual creep stage. These zircons also fence in the timeline on which any gentle plaster would have to occur if it were to become part of the far side's enduring shell, early enough to join the buoyant crust, or late enough to glide across a still-warm lid and stick. The mystery that lingers without urgency is whether any isotopic tracer can ever fingerprint a vanished companion explicitly. If the second orb is born of the same impact plume, its isotopic accent is the same. If it merges softly, it adds thickness without new chemistry. If an alternative tidal heating asymmetry or mantle overturn did the whole job, the chemistry still looks like Earth, because the starting material is Earth. Thus, chemistry can test origins of the disk, and the mixing in the aftermath can time differentiation with tungsten and zircon, and lead can inventory heat and volatiles with thorium maps and apatite, but cannot by itself command a verdict on 2 moons versus 1. Soft dry observations follow as a closing cadence only took a few parts per thousand in oxygen to tie a world to its parent more tightly than any other satellite we know. Only took trace water in microscopic crystals to rewrite a chapter title from dry to mostly dry. Only took Argon's drift at lunar midnight to remind everyone that even airlessness has seasons if one listens with the right instrument. Through it all, the narrative remains even samples on shelves keep their pale glow spectra from orbiters, continue to count elements by the photons they release. Gravity maps set crustal thickness beneath chemistry's colours, polar shadows hoard ices measured by neutrons, and the moon's accent stays stubbornly Earth-like in the systems that matter most. This sameness supports the giant impact origin, and leaves room for the gentlest version of a second companion, one that changes height but not speech. In the quiet of the room, the listener sits with an image that does not ask for brightness. A bead of volcanic glass under a microscope, a tiny bubble within it, and inside the bubble a few molecules that crossed 4 billion years without hurrying, carrying enough hydrogen to tilt an origin story by a sentence. Beside that bead on a different table lies a map that glows where thorium sleeps near the nearside basins, and a gravity inversion that says the far side is thicker and would have stayed aloof from seas. Chemistry and mass and light hum the same note. The moon holds still under one face and keeps the ledger open. Nothing insists and everything accumulates. Only took atoms counted to parts per million to soften a picture drawn in rock. Only took isotopes measured to 5 decimals to bind a satellite to its planet in the mind. Only took a breath from a grain to make a waterless world quietly admit it was never quite so. Modelling lost companions begins with numbers that behave like pebbles in a stream and ends with landscapes that do not move. In third person present the story walks from laboratory screens to lunar maps, where supercomputer experiments follow molten droplets as if they were stars and trace orbits as if they were threads in cloth. The scientific fact at the spine is undramatic, and central modern simulations of the moon's origin and early dynamics, smoothed particle hydrodynamics SPH for impact and disk, N-body and tidal models for orbital evolution, show that a giant impact plume can assemble multiple clumps beyond the Roche limit, and that co-orbital configurations including Trojan-like librations and horseshoe paths can persist long enough for gentle encounters to be plausible under reasonable tidal parameters. The impact itself in code is a silence full of arithmetic. Millions to hundreds of millions of SPH particles represent silicate vapor melt and metal. Equations of state anios, or its modernized variants, turn pressure and temperature into density and phase. The collision angles vary by degrees, the mass of Theia by tenths of an Earth mass, the spin of Earth by hours. With each variation, the disk's mass and temperature profile shift, and the newborn moonlet's feeding zone thickens or thins like a tide that obeys math but looks like weather. In some runs, a synestia, an overfilled vaporous donut-like state, forms briefly a hot envelope where rock behaves like gas, and where exchange between Earth and disk is so thorough that isotopes forget their separate accents before droplets condense. A lesser-known tactile detail keeps the scene human in these calculations, the smoothing kernel a bell-shaped weight function that decides how a particle listens to its neighbours, quietly controls whether the plume grains into clumps or smears into fog. A slight change to neighbour counts or to artificial viscosity can alter how fast droplets cool and stick, and those micro-decisions propagate outward until the disk either births a single dominant moon or litters the nursery with siblings that later merge. The result is not whimsy, but sensitivity managed by resolution and calibration against experiments and constraints. Once a primary moon is present in code, the problem spreads into space and time. N-body integrators hand positions and velocities to tides and tides, in turn hand energy back to orbits. Earth's tidal quality factor Q and love numbers, measures of how easily the planet deforms and how quickly it dissipates, set the cadence of lunar recession. Early Earth hot and ocean poor may dissipate differently than the blue planet does later. The models allow Q to vary with period and mantle state, and when that dial turns the outward march of the moon, and the evolution of co-orbitals change their pace like a metronome adjusted in mid-song. The quiet mystery that runs through this modelling is not whether code can make two moons for a while, it can, but whether nature did and for how long. Initial conditions are a forest, not a path impact angle. Thayer's core fraction, the disk's entropy, the partition of metal between Earth and plume, the sun's early luminosity, the planet's oblateness when spin is fast, the transitioning Laplace plane, the evolving ocean depth, the mantle's rheology. A landscape of viable births produces families of evolutions, and the models must be pruned by outside facts, crustal thickness from Grail, isotopic sameness, from labs chronology, from zircons and basalts, until only some histories remain attractive. The pruning is calm, iterative, and never quite done. Co-orbital companions in these runs live in neighbourhoods that look like ponds rather than points. Tadpole orbits around plus 60 degrees of the main moon's mean longitude horseshoe paths that span leading to trailing and back quasi-satellite loops that loiter near the primary sky. Solar perturbations warp the ponds. Earth's tides tilt the surface. Dissipation inside the small companion damps its eccentricity and inclination. Little by little libration amplitudes shrink, and the guiding centre slides toward encounter. Relative speeds, the crucial quantity, fall to hundreds of meters per second in favoured outcomes, a pace proper for plaster rather than shrapnel. 3 soft ironies gather on the console's glow the more precisely models can reconstruct a gentle merger, the more they predict a signature too subtle for easy detection. The simulations that most honour isotopic sameness purposely erase compositional contrasts that storytellers would love to find, and the codes that make the event possible also populate the alternative, no second moon, only thermal asymmetry, and cumulate geography with equal competence so success expands options before it narrows them. Evection resonance between the precession of the moon's perigee and Earth's orbital motion appears in many evolutions as a courteous siphon for angular momentum. If the initial impact leaves the system too fast, tidal torques and evection together can settle it toward today's budget. In co-orbital stories, evection can also reshape the companion's corridor pumping eccentricity before tides cool it again. Whether this resonance is visitor or resident depends on Q and on the disk's lifetime. Modelling treats it as opportunity rather than requirement and allowed route among others. A gentle modern analogy flows through the lab. The early Earth-Moon system behaves like a pair of dancers on a floating stage, while stage hands adjust the friction underfoot and the wind above. The steps are precise enough to teach the variations, numerous enough to forgive, and the final pose, the moon we know, can be reached by more than one choreography. A lesser-known, almost domestic detail ties numbers to stones. Gravity inversions from Grail are fed back into models as boundary conditions. thickness maps become masks against which outcomes are scored, runs that yield farside crust thicker by the right margin, nearside heat concentrations consistent with Procellarum and Mascon distributions that do not embarrass known basins receive better grades. The scoring is not a verdict, but a sieve that lets through histories most compatible with the quiet, stubborn relief of the real moon. In the laboratory corner, samples constrain time tungsten, 182 differences, or their absence define how long metal and silicate had to separate before the disk equilibrated. Uranium-led ages in lunar zircons draw lines around the cooling tails that models must honour. Water in apatite sets ceilings for volatile loss during the hot phase. Potassium and zinc isotopes testify to evaporation. Codes turn these truths into gates. This anestia must last long enough to mix, not so long as to strip every moderate volatile. The disk must cool quickly enough to condense crust early, not so quickly that creep cannot gather. A companion can add thickness without adding chemistry that does not already match. 3 more soft ironies flicker in the compile queue. The best fits to data often come from parameter sweeps that never existed in the sky, a humility baked into the method. The very instrument that proves a symmetry, precision gravity mapping flies, because previous missions were destabilized by that same asymmetry. And the second moon most people ask to imagine is in code, a statistical object that appears, disappears, and merges across hundreds of runs, visible only as a pattern in outputs, never as a single pretty picture. Far from the terminal's background solar system dynamics provide analogies that soothe doubt. Co-orbital asteroids of Earth, Mars, and Jupiter's Trojans demonstrate that shared orbits can last for long intervals under real solar perturbations. Binary rubble piles in the asteroid belt merge or tidally touch at walking speeds. Small moons of Saturn and Jupiter interact in horseshoe dances detectable by minute timing shifts. None of these proves the lunar case, but all confirm the grammar. Gravity writes the same kinds of sentences in many alphabets. A lesser-known technical note steadies expectations. Chaos does live in the problem, Lyapunov times for co-orbital motion. Undersolar tides can be short compared to the age of the system, but chaos does not equal noise. On top of chaos sit invariant Tauri and sticky islands where orbits linger for long spans. Dissipative forces like tides reduce the volume of available phase space and funnel trajectories toward low-energy endpoints. That is why a wide set of initial conditions can end in a gentle encounter even when any single trajectory cannot be predicted beyond a few libration periods. The ensemble is readable where the path is not. The mystery that remains after all this computation is disarmingly simple. What would constitute proof in stone? A buried suture under the far side highlands audible to a dense seismic array. A systematic bias in crustal anisotropy that maps a smear. A localized distribution of deep reflectors that trace a lobe. Perhaps. Yet each of these signatures can acquire alternate explanations. Cumulate, overturn, asymmetric tidal heating. Basin clustering. Modelling prepares a list of askable questions rather than a claim of closure, which is the proper endpoint for code that respects rocks. 3 final soft ironies close the notebook. The computing power that can evolve a hot disk into cold continents of crust cannot yet persuade a budget to put a seismic network on the far side, where the decisive test would be simplest. The neatest low-velocity mergers in code produce the blandest compositional results in labs, which means best cases draw the fewest headlines. And the most accurate way to retell a 4.5 billion year event is to run thousands of one-week jobs on machines that hum under fluorescent lights, epochs scaled down to office hours so that planets can keep appointments. In present tense, the models continue to learn manners from maps. Parameter studies tighten, priors narrow, the co-orbital companion remains allowed, occasionally preferred, never required. Alternatives remain healthy, sometimes hybridized tidal heating, plus creep plus plaster, because the moon has room for more than one influence, and the listener still in lamplight keeps company with a picture that is quiet, precisely where it is strongest, a disk that can make siblings a corridor that can keep them for a while, tides that can slow a meeting to a seam and a far side thick enough to remember an event whether or not it was the only way to reach that thickness. Only took kernels and equations of state to turn fire into droplets that behave. Only took Q and love numbers to make tides into editors. Only took gravity's patient corridors for a second moon to be possible, and polite enough to vanish into geography. Alternate histories of the far side gather in the room like colleagues who never raise their voices. In third person present, each speaks in a language of physics and evidence neither jealous nor triumphant, all content to coexist in the same slow orbit of thought. The scientific fact underlying them is that the moon's hemispheric difference's thickness of crust, concentration of radiogenic elements, the pattern of volcanic maria can be explained without invoking a lost companion, and that multiple mechanisms can sculpt the same contrast using heat time and geometry alone. One of these histories begins with the idea of tidal heating asymmetry. When the young moon orbits close to Earth, its synchronous face endures the planet's gravity as both anchor and sculptor. Internal friction converts flexure to heat, and that heating is stronger on the hemisphere facing Earth, the same hemisphere already bathed in radiant warmth from a glowing planet. The near side remains hotter for longer, its crust slower to thicken its mantle, more prone to convect, while the far side cooler and more insulated allows plagioclase to float and solidify faster, building thicker highlands. The mechanism needs no second moon, only proximity, viscosity and patience. A lesser-known detail gives it texture. Tidal dissipation within a body depends strongly on its thermal state and rheology, and the magma ocean. Stage provides an environment where small differences in temperature lead to large differences in heating. An Earth radiating at thousands of Kelvin through the early infrared adds a constant lamp of energy that exaggerates the imbalance. Numerical models by patient geophysicists show that within a few million years the far side can accumulate tens of kilometers more crust than the near side in a symmetry of the right scale, and sign achieved by nothing fancier than a hot planet nearby. Another history equally civil speaks of asymmetric crustal growth from the start. The moon's magma ocean does not freeze evenly. The distribution of radiogenic elements uranium, thorium and potassium may have been uneven in the liquid mantle due to convective currents, or concentrated by a process called cumulate overturn, in which dense titanium-rich layers sink and lighter, plagioclase-rich layers rise in patches. The result is a heterogeneous crust, whose thickest portions drift toward what becomes the far side through gravitational or rotational sorting. When cooling finishes, the near side inherits thinner crust laced with heat producers, the far side inherits thicker crust with fewer. The chemistry of Apollo samples and orbital gamma-ray data both tolerate this outcome. A quiet scientific mystery remains at its heart. Why would such heterogeneity align so neatly with the axis that defines the moon's tidal lock, as if nature preferred a hemisphere to a hemisphere rather than a random patchwork? Perhaps early locking itself achieved quickly when Earth's tides slow, the moon's spin aligns a pre-existing compositional contrast by gravitational potential. Perhaps the lock and the asymmetry are mutually reinforcing, each helping the other settle. A gentle modern analogy crosses the room and leaves a loaf cooling unevenly in an oven finds its crust thicker where the heat leaks slowest, and when turned toward the draft it will always show that face to the door again. Nothing deliberate, only feedback between heat and form. A third alternate story speaks through impacts. The early solar system's bombardment, heavy and prolonged, did not fall evenly. Models of orbital dynamics hint that large projectiles from certain resonant corridors between the giant planets could strike preferentially at longitudes facing the outer system, potentially biasing the distribution of basins. Giant impacts thin crust, locally elevate hot mantle, and in later ages provide paths for magma to flood basins. On the Moon, the near side's maria correspond to basins that overlap in time with the tail of this bombardment. The far side's highlands escaped some of that clustering, preserving older crust. In this telling, the asymmetry is not built in but written by chance by where the bullets came from, and when they stopped. A lesser-known observational note underscores its plausibility on Mars. Large impacts also triggered localized volcanism by thinning the lithosphere and promoting decompression, melting a planetary rime that strengthens the logic for the Moon's basins without needing exotic causes. 3 soft ironies drift like low dust between these theories. Every alternative that excludes a second moon still grants the far side special treatment, so the very feature used to argue against a twin affirms that something unusual happened. The explanations that rely most strictly on natural laws, heat diffusion, impact probability, require no speculation, yet produce results as asymmetrical and poetic as any myth. And the more careful the data become, the more likely it is that all of these mechanisms work together, each modest on its own but persuasive in chorus. Another history sits at the same table and adds a thought about radiogenic inheritance. The distribution of creep, the residue of incompatible elements from the magma ocean, is not symmetrical. Mapping of thorium from orbit shows concentration on the near side in a region called Procellarum, while the far side is poor in those elements. If the Procellarum creep terrain acted as a localized furnace for billions of years, it could have kept that hemisphere softer, thinner, and volcanically active long after the far side froze. The origin of the terrain's boundaries might relate to early stress fields or to a frozen-in shape of the lunar core mantle boundary. Thermal modelling with such a furnace reproduces late mare flooding and matches the timing of basalt eruptions measured by radiometric dating of returned samples. A lesser-known tactile detail from those samples whispers agreement potassium-rich glass beads and high titanium basalts both hail from near-side sites, confirming that the heat engine preferred one domain. The creep model does not forbid gentle plaster or tidal asymmetry. It complements them, showing how early differences could be magnified over time. The conversation among models becomes almost familial. Each offers one layer, and the Moon in its quietness may have accepted all of them, stacking asymmetry upon asymmetry until the pattern became permanent. The quiet mystery that persists beyond these variants concerns timing. Did crustal dichotomy appear during solidification before the late heavy bombardment, or after it? Evidence from crater counts and basin stratigraphy suggests early formation before 4.3 billion years, but precise ages blur near the magma ocean's last gasp. If thickness differences arise too late, they cannot explain where Maria later erupt. If too early, they must survive every blow. Models can accommodate both schedules by adjusting tidal evolution and heat flux. The Moon stays patient as equations argue in silence. 3 more soft ironies glide through this cool debate. The more mechanisms are found sufficient, the less any single one can claim necessity. The farther into detail the data reach, the more they resemble a sketch rather than a photograph. And the name farside, which once meant distance, has become shorthand for the hemisphere, where we are closest to understanding origins, because asymmetry is clarity disguised as unevenness. A lesser-known measurement binds all histories together. Crustal thickness and gravity anomalies correlate with the distribution of thorium and uranium, only loosely suggesting that while radiogenic heating shaped later events, the primordial thickness pattern owed much to earlier structural conditions. This modest mismatch keeps every explanation humble. A gentle analogy arises. The Moon's faces are like 2 pages printed from the same plate, but inked differently, one pressed harder, one more lightly, both legible, both true. Seismic studies, limited though they are to near-side stations, indicate a crust mantle boundary, shallower under Maria, deeper under Highlands. Farside data inferred from gravity align with that gradient. Together they make a picture consistent with any mixture of tidal heating, radiogenic asymmetry, and even mild plastering. The point is not choice, but coherence. The listener in the room feels how calm this multiplicity becomes. The Moon allows parallel explanations without argument, because all are grounded in measurable physics, and all meet the same map without contradiction. The section closes not with verdict, but with reflection. Alternate histories form a slow chord that sustains the main theme, Earth and Moon, as a system that learned symmetry only in motion and difference only in stillness. The quiet endurance of these models underscores three final dry observations only took the same laws of conduction radiation and chance to produce an asymmetry people still call mysterious. Only took several sufficient answers to remind science that enough can coexist with maybe. Only took one half of a face kept permanently hidden to teach that consensus is not the only form of peace. Echoes in other worlds move like low music through the solar system, and in third person present the moon's possibilities are held up to neighbours and kin places, where co-orbital dances, gentle mergers and hemispheric asymmetries appear under different lamps, all speaking a grammar that feels familiar even when the nouns change. The scientific fact that steadies this tour is plain multiple moons coalesce, share, orbits trade places and sometimes meet. Debris disks around planets form satellites. Impacts make companions, and tides rewrite distances. The Earth-Moon story is one version of a broader script that plays across many stages. Around Saturn, a small performance repeats endlessly. Janus and Epimetheus share almost the same orbit and execute a horseshoe dance trading positions every few years, with relative speeds so low that their mutual encounters are courtly rather than violent. The existence of this duet proves that co-orbital niches are not abstractions but lived in addresses where gravity permits long companionship without collision. A lesser-known tactile detail in that theatre, when Janus and Epimetheus approach their mutual tug shifts each by only a few tens of meters per second, a speed one could run across, yet the outcome who is inner, who is outer, reverses an orbital handshake that feels like a lesson in how small pushes can govern large labels when geometry is kind. Saturn offers other co-orbitals named less often in conversation, Trojan moons riding ahead of and behind Tethys and Dion Telesto, Calypso, Helen Polydeuces, still small worlds gathered where the three-body problem carves safe coves. They endure as counterpoints to the Earth-Moon speculation, a reminder that second companions can exist for billions of years, given the right mass ratios and tides. Jupiter keeps a nation of Trojans at plus just 60 degrees from its orbit. Not moons, but asteroids bound to a shared year. Mars hosts its own Trojans, and Earth too keeps a small population. The echo is consistent, shared paths are common in celestial mechanics, and long pauses before decision are normal. The gentle analogy writes itself and leaves a highway with wide shoulders, allows slow cars to drift along beside each other, sometimes trading lanes without bumpers ever meeting. Whether they merge into one lane depends on the grade, the patience of drivers and winds that nobody set. In the country of impacts, Pluto and Charon repeat a portion of Earth's story with a different accent. A giant collision likely throws debris that becomes a binary with Charon so large relative to Pluto that the two lock each other and circle a shared barycenter. In empty black, a visible memorial to angular momentum's habit of spinning companions into stable duets. The smaller moons, Nix Hydra Kerberos, and Styx faint shards of the same episode orbit farther out their rotations, chaotic their surfaces bright. Another family of survivors coaxed into order by time. A quiet scientific mystery lingers. Even here did those small moons grow by gentle sticking in a cool disk, like scaled-down comets, or by reassembly of collision splinters in a vacuum with little dust. Their irregular shapes and water ice spectra give hints, not verdicts. The ambiguity rhymes with the moon's own subtler questions about plaster and heat. Closer to home, Mars keeps two small satellites, Phobos and Deimos, long regarded as captured asteroids, but now argued by some models to be born of an impact disk that later thinned to faint rings, a thought that makes the red planet a modest cousin to Earth in moon-making. Phobos spirals inward today and will fail in tens of millions of years perhaps to become a ring before raining down a reminder that not all companionships last and that tides can unwrite what orbits once wrote. Three soft ironies drift through this Martian scene, the moon that seems most permanent to our eyes. The moon itself owes its stability to recession, while Phobos, which looks safest tucked in close, is doomed by the very torque that holds it. A ring may be the late echo of a moon, not always the prelude, and the planet least like Earth in size, Pluto ended with the most Earth-like moon story and structure, impact disk binary scaled and frozen into a distant duet. Elsewhere, Saturn's ring moonlets tiny shepherds like Pan and Daphnis illustrate how material can gather in gaps and remain intact under steady perturbations. Their ridges of accreted ring snow show that in gentle environments, mass can adhere without melting a low-temperature cousin to the plaster imagined for a second moon. At the same time, Iapetus Saturn's yin-yang world keeps a dramatic albedo dichotomy, dark Cassini regio facing forward, bright trailing hemisphere likely a combination of exogenic dust and thermal migration of ice. A hemispheric contrast born not of thickness or second companions but of surface physics. Asymmetry comes in many dialects. A lesser-known, almost domestic note in that tale, dark dust, likely drifts from retrograde Phoebe and is swept up by Iapetus's leading hemisphere, where increased absorption warms ice enough to hop molecules toward colder terrain, a runaway that writes a permanent two-tone face-proof that a simple feedback in light and temperature can make hemispheres differ without touching the interior. The giant planets teach a catalogue of formation modes. Many outer satellites are captured irregular, inclined and retrograde scraps of early migration, folded into parking orbits by chance and drag. Inner regular satellites grow in subdisks like small planetary systems. Some pairs, like the co-orbital duo around Saturn, move in low-velocity corridors. Others likely merged long ago, their signatures erased by depth. The point is not to claim the moon's exact method at every address, but to recognise that similar physics impact disk co-orbital niches. Tide is fluent throughout. A quiet scientific mystery returns to the central hypothesis in this mirror. How commonly do slow mergers leave readable sutures? Small binaries in the asteroid belt sometimes show contact shapes, two lobes melded like snowmen, implying low-speed unions that preserve necks. Comet 67P Churyumov-Gerasimenko wears such a neck. Arakoth beyond Pluto carries the same hourglass, yet these are bodies of rubble under a whisper of gravity. On larger differentiated moons, soft impacts likely smear into crustal thickness without contour. The very scale that ensures plausibility erases the photographable evidence, perverse generosity that allows many cases and confirms few. 3 more soft ironies settle like quiet ash. The cleanest examples of gentle mergers appear at sizes where nothing is layered enough to record them well, while the world's layered enough to hold a memory would hide it. The best present-day demonstrations of co-orbital dances that could precede such mergers, Janus and Epimetheus, seem to be precisely the pairs least destined to collide, and the strongest hint that multiple moons can emerge from one disk. Pluto's family ends with a configuration where the big merger never happened, only the big binding. Beyond our system, hints multiply but remain cautious. Exoplanet-like curves occasionally show dust rings and circumplanetary features that could be moon-forming disks. One candidate around the young planet, PDS-70C, likely hosts such a subdisk, a cradle for satellites in the act of being. If common, then the path from impact or inflow to multiple moonlets and occasional mergers is not exotic, but ordinary in cosmic neighbourhoods, where gas and dust still remember how to spin. The gentle analogy that follows is simple. The solar system is a library where one finds many editions of the same book, some annotated, some abridged, some with pages glued together by time, and the moon is one printing among many. The words gravity, heat, collision. Tides stay the same even as the margins change. A lesser-known tactile observation links back to Earth the pattern of tidal recession written in ancient terrestrial rhythmites, laminated sediments that show daily, monthly and seasonal cycles, demonstrates that our moon's distance and Earth's day were once different. Similar paleotidal signatures should exist for other planetary pairs in principle, but only Earth keeps rocks with oceans and calendars to record them. The rest of the family is silent on paper, even as it obeys the same metronome. The section's quiet mystery returns once more to the far side. Do any other moon show hemispheric thickness, contrasts of the same magnitude? And if they do not, that make the moon's story rare or only lucky in visibility. Grail-class gravity for other worlds is scarce. A far-side network on the moon would make even better comparisons at home first. Until then, asymmetry remains most legible here, not because it is unique, but because instruments have stared longest. 3 final soft-dry observations complete the circuit. Only took a pair of small co-orbitals around Saturn to show that long low-speed meetings are mechanically respectable. Only took Pluto's family to prove that one violent event can plant a permanent orderly clan of moons without ruining isotopic temperaments. By analogy, order after impact is natural. And only took Mars's uneasy Phobos to remind everyone that tides can either lengthen companionship or schedule its end the same tool, writing harmony and goodbye by changing one sign in the ledger. Through all of this, the moon's possibility, once 2 now 1 thickened, feels less like an exception, and more like a variant. The solar system speaks many accents of the same laws, and the echoes make the room calmer, not busier. The Earth-Moon pair remains singular in detail and ordinary in grammar, a companion born from heat and spin, a history that tolerates siblings and mergers, a face that keeps asymmetry as memory, and a present that reads as balance. Only took other dancers to show that our steps are not strange. Only took a few shared corridors to make a second moon thinkable. Only took the distant hush of binary dwarfs and Trojan beads to make coasts of possibility appear on a map of one familiar sky. The long sleep of stone begins after all movement ends when the tides have finished their work, and the last companion, real or imagined, has folded into a single sphere that drifts outward from Earth like a slow-held breath. In third person, present time slackens. The moon is now a solitary body, tidally locked its synchronous face forever, watching the planet that raised it. The scientific fact at the spine is clear and durable. Tidal friction between Earth and the moon transfers angular momentum outward, lengthening Earth's day, and increasing the lunar orbit's semi-major axis by roughly 3.8 centimeters each year, a figure measured today by laser pulses reflecting off corner cubes left by Apollo astronauts. Over billions of years, that gentle recession changes perspective. When the moon first formed, it may have hung 10 times closer. Its apparent diameter, enormous tides hundreds of times stronger. Its orbital period measured in mere days. Now it circles at 384,000 kilometers, taking a month to return to its start in sky. The process is continuous, governed by torque viscosity, and the phase lag between tidal bulge and gravitational pull. A lesser-known tactile detail folds quietly into this expansion. Each centimetre of lunar recession corresponds to heat generated within Earth's oceans, and crust dissipating mechanical energy as turbulence, friction, and mixing. In this sense, every tide that laps a modern shore is the faint echo of the original torque that once may have made 2 moons merge. Each wave breaking on sand is a molecule-level version of the same energy exchange that keeps distance growing. The quiet scientific mystery remains whether this gradual drift has always been so steady. Paleontological rhythmites, ancient sedimentary laminations recording tidal cycles suggest that 620 million years ago, Earth's day was about 21.9 hours, and there were 400 days in a year, implying faster recession then. Earlier rocks, older than 2 billion years, hint at different rates and models, show that ocean basin geometry, continental drift and resonance can modulate dissipation over geological ages. The moon's outward motion therefore is not a metronome, but a breathing curve quickening and slowing as the shape of Earth changes. 3 soft ironies move through the arithmetic. The more the moon pulls energy from Earth, the farther it drifts and the weaker the tides become. So each act of connection ensures future distance. The very friction that slows our planet's rotation prolongs its days into comfort for life, but also erases the fast rhythm that first raised the moon high, and the more precisely the rate is measured, the more clearly it reveals that absolute stillness, tidal equilibrium, where one face of Earth would always watch. One face of moon will never be reached before the sun expands and ends the experiment. In this epoch of settled stone, the Moon's orbit stabilizes near its current tilt, about 5 degrees to Earth's plane, so that eclipses still happen, but not too often a balance between chaos and order. Its crust thickens by cooling seismic energy, wanes, and contraction wrinkles the Maria into low ridges. The far side keeps its mountainous dignity, the near side its plains. A lesser-known note of quiet activity persists beneath the stillness. Shallow moonquakes still occur, some registering magnitude 5 caused by tidal flexure or thermal expansion as day follows night. Lobet scarps, small cliff-like features creep across craters where the crust is shortened by cooling. These modern stirrings remind geologists that even in apparent rest, the Moon is not frozen beyond change, only slow enough to count as eternal for human scales. The long sleep of stone includes the decline of bombardment after the late heavy bombardment, faded impacts dwindled to sporadic visitors. Micrometeorites grind the surface into regolith, a powder of shattered glass and rock shards that thickens by millimeters per millennium. Each grain holds the imprint of space, weathering solar wind ions, implanted cosmic rays splitting atoms, nanophase iron particles darkening reflectance. This garden of dust renews itself in place, churned by every new arrival, a record without writing. 3 dry observations drift from this quiet surface only took 500 million years of peace to make a desert look timeless. Only took micrometeorites the size of sand to erase mountains faster than they grow, and only took vacuum and time to turn the roughness of youth into the soft round limb that rises over Earth's horizons tonight. Beneath the crust mantle, convection has long ceased. Any core dynamo faded billions of years ago, leaving only remnant magnetization in certain rocks. Magnetism recorded when basalts cooled in the presence of an ancient field that no longer exists. The mystery remains how such a small core, only a few hundred kilometers wide, generated that field. Possibilities include mechanical stirring from impacts or crystallization of an inner core releasing light elements into a liquid outer core. Whatever its engine, it stopped, and the Moon now drifts magnetically silent through space. Its field a ghost measured in weak nanoteslas by orbiters. A gentle analogy hums through this magnetism. It is like a bell that once rang when struck by formation, and now resonates only through the metal it left behind. The sound no longer travels, but the shape of the bell remembers having sung. The long sleep is not total uniformity. The Moon's libration, its slight wobble as it orbits, lets Earth-based observers see 59% of its surface over time. The rest, the true far side, remains hidden until orbiters carry cameras. This geometry, a product of synchronous lock and elliptical orbit, is an old compromise between torque and inertia. It keeps the Moon's same face turned roughly toward Earth, while letting the view breathe at the edges. The far side's hiddenness is now relative spacecraft have mapped it in detail gravity field, measured to milligal precision, yet psychological distance persists. Humans continue to call it dark, though it receives equal sunlight, a linguistic residue of ignorance that outlasts its cause. 3 more soft ironies move through the airless night. The hemisphere, once imagined as invisible, is now the best mapped body in the solar system. The light we reflect from it to Earth's telescopes reveals not darkness, but overwhelming familiarity, and the longer humanity stares, the clearer it becomes that mystery itself is renewable even when knowledge grows. In this settled age, the Moon's relationship with Earth becomes a long mathematical friendship. Its recession affects tides, tides affect climate. The drag of oceanic friction shapes wind patterns and sediment cycles. Paleoclimate records show hints of Milankovitch rhythms, subtle oscillations in obliquity and precession, modulated by the Moon's gravitational presence. Without it, Earth's axial tilt might wander chaotically, seasons fluctuating wildly. The Moon's stability acts as a gyroscope for climate habitability, a fact dryly miraculous and often overlooked. A lesser-known connection extends further. Coral growth bands and tidal rhythmites in ancient formations reveal that life has followed the Moon's rhythm since long before minds noticed it. Some fossils record daily or monthly cycles in their shells, silent witnesses to a partnership older than any word for time. The long sleep then is not death but maintenance, a slow geophysical meditation that keeps Earth's tilt steady enough for seasons, tides mild enough for shorelines, nights long enough for reflection. The same torque that once might have pulled two moons together now threads this equilibrium. A quiet scientific mystery lingers at the edge of imagination. If someday billions of years hence tidal evolution reaches a point where Earth and Moon become mutually locked, Earth's day equal to the Moon's month, then one hemisphere of Earth would always face the Moon, and the other would never see it. Tides would stop, climates would reshape, and the sky would fix. Such synchrony is theoretically possible, but cosmically unlikely, interrupted long before by the Sun's red expansion. Thus the partnership ends not by quarrel but by a greater warmth arriving. Three final soft ironies close the page, only took friction to preserve balance. Only took the slowest dance in the solar system to sustain the fastest living rhythms below. Only took a few centimetres per year to move the Moon from a newborn blaze to a companion that now appears to move slow enough for poetry. In the quiet of this epoch, the Moon rests in its orbit, turning with a patience learned from oceans, carrying the asymmetry of its birth as a pale watermark across its far side, and shining every night on a planet that cannot remember the world before its light. Listening to the Highlands is an act of patience, not discovery, and in third person present, the Moon lies still while instruments extend senses where ears and eyes cannot go. The scientific fact anchoring this section is clear. Since Apollo, humanity has recorded moonquakes, mapped gravity at kilometre resolution, and modelled the internal layers of the Moon, yet the far side, where the crust is thickest, remains acoustically silent, never wired for seismic return. The data we have come from a handful of seismometers, all on the near side, whose signals must be deconvolved through crustal asymmetry and later impacts. The far side, where a second moon might have joined, or where the crustal plaster thickened, has never spoken directly. A lesser-known tactile detail rises softly from these old recordings. The Apollo passive seismic experiment from 1969 to 1977 detected thousands of events, meteoroid impacts, deep moonquakes, shallow quakes and thermal creaks, as surface rocks expand and contract in day-night extremes. Some deep quakes repeated monthly at depths of 700 to 1200 kilometres, synchronized with tidal stresses, proof that the Moon's interior still flexes in rhythm with Earth's pull. Even this distant heartbeat matters, a reminder that solid bodies breathe differently, but breathe nonetheless. The quiet scientific mystery keeps its tone level. What structure hides beneath the far side's mountainous shell? An ancient impact remnant, a buried suture, or only variations in composition, frozen from magma currents that never mixed. Gravity data implied denser material at depth near the near side's mascons, and lighter, thicker crust under the far side but without seismic travel times. To confirm, models must infer layer thicknesses indirectly. Grail's twin orbiters in 2012 mapped minute variations in acceleration, translating orbital wobbles into subsurface clues. They revealed crustal thickness variations from roughly 30 to 60 kilometres the thickest, under the far side highlands. They also found small circular mass deficits that may represent ancient collapsed voids, ghost basins hidden beneath younger impacts, offering a subtle test of whether those regions are the unspoken edges of a vanished companion. Three soft ironies linger beneath this analysis. The quietest hemisphere is the one most in need of listening. The tools sensitive enough to weigh a crustal anomaly from orbit cannot yet place a microphone on its surface, and the asymmetry most visible to telescopes remains the least sampled by seismology, as if the Moon insists that some answers require silence. Plans for far-side seismic networks now rest in proposals and prototypes. Next-generation landers, carrying geophones designed for the cold, thin regolith radio relays at Lagrange, points to send data home through the blocked line of sight. These ideas wait for funding patient as basalt. When they come, they will measure crustal discontinuities P and S wave velocities and the faint whisper of moonquakes travelling under mountains older than continents. A lesser-known poetic detail ties gravity and seismology together. Variations in free air gravity correlate with topography, but also with mass distribution at depth. On the far side, the correlation weakens slightly, suggesting internal layering too complex for uniformity. Some models simulate a mantle wedge or frozen asymmetry in heat-producing elements just below the crust-mantle boundary, perhaps a remnant of early convection cells or of the plastered shell from the two-moon scenario. The differences are measurable yet subtle kilograms per cubic metre. Here, kilometres of crust there, but over global scales such minutiae define mountains. The quiet analogy that drifts through this data work is of a heart heard through walls. Signals arrive filtered, echoes tangled. The scientist must reconstruct rhythm from reverberation. Every model of the far side's interior, be it thicker crust from differential cooling, a built-up seam or a symmetry in deep mantle composition, produces testable patterns in gravity anomalies and seismic wave travel times. The task is simply to listen long enough and to plant instruments where no air transmits sound but stone does. 3 soft, dry observations arise from this discipline. Only took a handful of seismometers left half a century ago to measure the size of the core. Only took microgal variations in spacecraft acceleration to draw the crust's thickness map. Only took silence on one hemisphere to keep curiosity alive across generations. In the calm of research, even small signals become companions. Every moonquake recorded, every impact pulse reflected through layers helps refine densities and depths. In these data, the moon becomes a laboratory of planetary cooling, a textbook on how small bodies retain heat and how symmetry decays into individuality. A lesser-known discovery tucked into these records adds a soft pulse of awe. The moon likely has a solid inner core about 240 kilometers wide, and a fluid outer core roughly twice that enveloped by a partially molten boundary layer. These estimates come from reprocessing Apollo data with new inversion techniques decades later, showing that even archived whispers can yield fresh sentences when listened to differently. The presence of a molten layer, however thin, keeps the possibility of faint core convection alive. Its heat budget derives from radioactive decay and from the residual warmth of formation. If it exists, it connects the moon faintly to its fiery youth, a thermal echo crossing billions of years. 3 further soft ironies settle like dust in a beam. The most up-to-date understanding of the moon's deep heart came not from new instruments, but from re-listening to tapes once considered exhausted. The knowledge that the moon has a small molten ring at depth coexists with the image of its cold, silent surface. And the structure that seems static in photographs is still vibrating faintly beneath its own gravity, proving that stillness and motion can coexist indefinitely. The idea of listening expands to electromagnetic ears. Orbiters have mapped crustal magnetism, revealing patchy fields, up to hundreds of nanoteslas, remnants of an ancient dynamo that ceased more than 3 billion years ago. Many of the strongest anomalies cluster along antipodes of large impact basins, perhaps formed when shock waves focused through the core and aligned metallic grains as they cooled. If a smaller companion ever merged into the far side, its impact could have generated similar transient fields, leaving patchy magnetization as testimony. A gentle analogy rises and fades. Magnetized crusts are like fossil songs, each domain a note from a vanished orchestra of molten metal. The far side's crust, thicker and less basaltic, may have retained these signatures differently, shielding some, erasing others. New magnetometers aboard orbiters map these scars with precision too fine for human metaphor. The quiet scientific mystery that closes this phase asks what the moon's deep silence would say, if fully heard, whether a layer boundary betrays an old collision seam, whether anisotropy in seismic velocities marks a buried ridge, or whether the entire dichotomy of near and far simply froze into place as cooling locked the first imperfections of convection. The answers remain possible but unsolved. 3 final soft ironies pass through this meditative measurement. Only took mechanical ears on a dead world to remind us that silence is data. Only took reanalysis of decades-old signals to learn that the core still murmurs. And only took a hemisphere that never faces Earth to prove that ignorance can be luminous. In the still orbit, the moon turns as always, its far side carrying a secret that may be mechanical, chemical, or imaginary, but remains disciplined by physics. The instruments rest awaiting successors. The dust lies calm over them. No breeze, no decay, only fronds to age them. To listen to the highlands is to accept that some questions will outlive their questioners, that waiting itself is part of method, and that patience can be a form of observation. The moon continues its quiet orbit, dragging tides and minds alike, holding its thickest crust against the sun, keeping its seam invisible, its echoes faint but eternal. A quiet rest under one moon begins with the same orbit that has persisted through every theory, the single companion circling a turning planet, bound by gravity, patient through change. In third person present, the world moves beneath a light that has forgotten violence. The scientific fact at the centre is simple and profound: the moon's evolution, whether from one collision or two from a symmetry, or from chance, has reached equilibrium, a stable synchronous rotation, a nearly circular orbit, and a constant relationship with Earth's tides. No new moons form, no companions remain to merge, only the ancient outcome endures. A lesser-known tactile detail lingers in this quiet geometry. The moon's orientation wobbles by degrees, librating in longitude and latitude as it swings through its slightly elliptical path, showing Earth about 9% more of its surface over time. These wobbles let astronomers refine gravity harmonics, measure mascons, and model interior structure. To the listener, they simply mean that the moon breathes gently a slow oscillation, keeping both sides alive. The quiet scientific mystery that hums under this stillness is not about formation anymore, but about memory. How long can a planetary body remember its birth? Thermal modelling suggests that deep crustal heat from radioactive decay still leaks out today, at a rate of about 18 milliwatts per square metre, measured by Apollo heat flow probes. Over eons, that trickle has cooled the mantle, shrunk the radius by roughly 100 metres, and folded the crust into scarps, wrinkles of contraction, visible in high-resolution orbital imagery. Each scarp is a sentence of cooling stone, unhurried, exact. 3 soft ironies rest in these measurements. The moon still moves, though too slowly for human patience. It still changes shape, though we call it unchanging. And the same heat that once made magma oceans now warms senses by fractions of a degree, proof that endings never end. The far side highlands, thick and pale, remain untouched by seas. The near side's basaltic plains gleam darker in low sun. From orbit, their contrast is not moral, but thermal albedo and mineral content writing history into colour. Earthshine paints both sides, at times the planet's blue light, softening craters into ghostly relief. The moon, in this present tense, is no longer forming or colliding. It is maintaining, orbiting, eroding by micro-impacts, recording solar wind in its soil. Every grain of regolith on its surface contains solar history helium-3, implanted by protons, records of ancient solar storms, isotopic signatures of galactic rays. The moon has become an archive that never overwrites itself. A lesser-known scientific grace note completes that thought deep within permanently shadowed craters near its poles, volatile ices have accumulated layer upon layer, perhaps preserving the chemical fingerprints of comets and asteroids over billions of years. These icy deposits are more than resources, they are stratified time stacked in frost each layer, an unspoken remembrance of the solar system's weather. To call it rest is accurate but incomplete. Rest is not emptiness, it is storage. The quiet analogy fits easily. The moon is a sleeping historian, its pages written in dust, its dreams illuminated by a planet it stabilizes. 3 soft ironies settle around that metaphor. The world that looks most lifeless contains the longest memory. The object that steadies Earth's axis is itself forever moving, and the companion that seems pale only reflects the light of oceans it helped keep calm enough for life to arise. In the contemporary sky, our laser beams from Earth still strike retroreflectors left on its surface, returning in a few seconds, measuring distance with millimetre precision. Those photons invisible to the eye tie planet and moon in a permanent conversation. The moon's gravity continues to moderate tides, sculpt shorelines, influence climate through subtle orbital cycles. Its slow outward drift lengthens Earth's day, allowing atmospheric drag and biological rhythms to co-evolve. These facts are quiet but enormous. Every day's length owes part of its extra light to the same tidal breaking that once may have merged two moons. The stillness in this epoch is not silence but resonance. The quiet, scientific mystery that remains open is emotional rather than mechanical. Why among all the planets and satellites does this one relationship evoke belonging? Perhaps because its pace matches ours. The moon's phases divide the night into visible increments, teaching time to species that could not yet name it. Its constancy reminds a restless biosphere of cyclical calm. Theories about lost companions, gentle mergers, and thermal asymmetries enrich rather than disturb this peace. They show that behind calm surfaces lie long lawful histories. Each possibility, two moons, one collision. Many causes ends here in one orbit that endures, because nothing in physics insists on ending it. 3 final, soft dry observations rest at the close. Only took gravitational patience to turn chaos into stability. Only took 1 billion years of slowing to write a calendar into the sky. Only took dust, silence, and light to prove that permanence can emerge from impact. The moon remains the Earth's witness and mirror, the last bright relic of formation. It circles, recedes, reflects, and waits its thickened crust, still holding the geometry of an encounter that may or may not have happened, but that left beauty as evidence. The far side faces away, the near side faces us, and together they form a system both mechanical and meditative. In the end there is only this, a world of rock, a sphere of water, a bond of gravity, and a long, slow equilibrium that feels like peace. The orbit continues, the light persists, and in the stillness of their shared motion, nothing is lost, only transformed into the quiet memory of stone.